In this section, we'll cover everything you need to know to get started with MongoDB on Linux or Windows. This will include how to identify the correct download for your platform, how to install MongoDB both manually and using packages, how to configure MongoDB so that it starts automatically when you boot your system, and finally, how to access and work with data in your MongoDB database. We need to install MongoDB so that we can begin to store and retrieve data. Let's see how this is done. For this course, I'm using cloud servers. For Linux, I'm using a DigitalOcean Ubuntu server running version 14.04 LTS. It has 512 megabytes of RAM and one CPU. For Windows, I'm using an Azure Cloud Server running Windows Server 2012 R2. It has 768 megabytes of RAM and a single shared CPU. In this video, we'll focus on downloading and installing MongoDB on Linux. The MongoDB website provides binary downloads for various versions of MongoDB. When you get to the home page, click the Downloads link. You'll notice that for Windows and Linux, there are a number of options. The most conspicuous is the choice between 32-bit and 64-bit operating systems. It's easy to find out whether you have a 32 or 64-bit operating system installed. On Linux, the uname command with the -a argument will output how many bits your operating system is. You can see here that we're running on a 64-bit operating system. Back on the MongoDB website, we can now identify the correct download link. We'll right-click and choose Copy Link Address to get it on the clipboard so we can download in just a minute. First, let's look at a few of the implications of the version of MongoDB that we choose. Note that not all MongoDB features are available in the 32-bit version. The 32-bit version is further limited in that the maximum database size is 2 gigabytes. For big data applications, this could be a roadblock. I generally prefer to stay close to the latest release for security and stability. For the quickest install possible, I always try to download directly to the system where I plan to install. MongoDB supports SSL, but their binary distributions don't come with SSL enabled. This means it's necessary to build Mongo from source to enable SSL support. That process won't be covered in this video, but will be covered in a later video. On Linux, we can use curl or wget to download the files. Since we copied it to the clipboard, we can just type in wget, and paste in the URL, and hit enter. The amount of time this takes to download will depend on your server, but most cloud servers have a pretty fast connection. For this first part, I'm demonstrating a manual installation. Later in this same video, I'll show you how to install from a platform-specific package. Now we need to unpack the files. We can combine the untar and gunzip processes with a single tar command using tar xzvf and the file name. This leaves us with a directory in our user directory that has all the MongoDB binaries. Note that no special privileges are required to run MongoDB. Before we can run MongoDB, we need to create paths where MongoDB can store logs and data files. We start by using makedir to create the data directory, and then we run another makedir command to create the logs directory. We can use ls-la to confirm that our data and logs directories were created the way we expect. A configuration file is necessary to provide the MongoDB process with the path to the logs and data directories. MongoDB configuration files conform to YAML, which makes them easy to read. Since we put our logs and data in the Mongo directory, that's a convenient place to create the configuration file. There are many options you can include in your configuration file. For now, the most important are the paths to the logs and the data directories. Now we can start the MongoDB server process and identify the config file that it should use using the ---- config option. We'll leave MongoDB running in this terminal and open another terminal window to verify that it started up as we expect. The first place I look is at the running processes by grepping for Mongo. We can see that process 1053 is running. and it identifies the correct configuration file. Note that the process is running as root, but that's because we're logged in as root. Next, I look at the log files using the tail command. We put those in Mongo logs, and we have the mongodb.log. If there were any errors on startup, they would print out here. This shows us that there is a currently running process and that there were no errors. Note that the process is running as root only because we are currently logged in as root. If everything looks good in the logs and from a process standpoint, it's easy to connect to the locally running MongoDB instance using the mongo command. Since we didn't change any of the default paths, ports, or other connection details, and we're on localhost, it's not necessary to provide any details. It's not necessary to provide any details to connect to the MongoDB instance. Now we're successfully connected. In this manual install, we have skipped over a number of details that will be important for a production deployment. These include creating a script to start the Mongo process with desired run levels, meaning it will start automatically when the server boots, running the MongoDB process as an unprivileged user, and properly assigning permissions and ownership for related files. For stability, you'll also want to use a tool like logrotate to prevent using up all disk space storing log files. As you'll see in a minute, most of these concerns are taken care of for you when you install using the package method I'm about to show you. Let's clean up a bit so we can demonstrate the package installation. First, we'll exit out of the Mongo client, and then we can close this terminal window. We can also kill the MongoDB process by typing Control-C. Using the same techniques we used above to confirm that MongoDB started successfully, we can confirm that the process is no longer running. First, we do a process command and grep for Mongo, and we see that the process is no longer running. We can also do a quick tail on the log files and see that it says db exit, really exiting now. At this point, we can clean up the files from the manual installation and start fresh. And there's one more file there that we want to remove. Now our directory is clean. In order to install using the package method, we need to set up our server to communicate with the package repository. We start the process by importing the public key for that repository. With the public key imported, we can update our package list and create a local package database for installation of MongoDB files. And now we update the local package listing using sudo apt-get update. Now we can use the system-provided package management tools to install MongoDB. In this case, we use apt-get. Packages can be installed separately for the MongoDB server, client, tools, sharding service. The MongoDB org option installs the entire collection. So this command will install all of MongoDB. After installing the packages, the MongoDB process should already be running. We can confirm that the MongoDB process is running, just as we did before using the process command. Sure enough, we see it there with process ID 1594. Notice that the MongoDB process is now owned by a normal user, MongoDB, not root. The logs are now managed in the standard location, and logrotate will ensure they don't get out of hand. We can tail the log to look for any errors with tail var log mongo. This shows that Mongo started up as expected. Finally, we can connect to Mongo using the normal client. Notice that the MongoDB binaries are now in the path. In this video, we have identified our operating system and that it was 64 bits. We installed MongoDB using two processes, manual and package-based. We also learned 3 ways to verify the MongoDB process is running, by viewing processes, viewing the logs, and establishing a connection. In the next video, we'll go through the process to install MongoDB on Windows. In this video, we'll focus on downloading and installing MongoDB on Windows. Throughout this training, I'm using a Windows Server 2012 R2 system running on Microsoft Azure. The MongoDB website provides binary downloads for various versions of MongoDB. When you get to the home page, click the Downloads link. You'll notice that for Windows and Linux, there are a number of options. The most conspicuous is the choice between 32-bit and 64-bit operating systems. It's easy to find out whether you have a 32-bit or 64-bit operating system installed. For many screen windows, move your mouse to the top right, revealing the Charms bar. Click on Settings and Server Info. The window that comes up has a line titled System Type, which indicates whether you are running 32 or 64 bits. In this case, we're running 64 bits. Back on the MongoDB website, we can now identify the correct download link. We simply click the download link to start the download right away. I choose to save the file, and while that's downloading, let's take a look at a few of the implications of running the version of MongoDB that we're interested in. Note that not all MongoDB features are available in the 32-bit version. The 32-bit version is further limited in that the maximum database size is 2 gigabytes. For big data applications, this could be a roadblock. I generally prefer to stay close to the latest release for security and stability. For the quickest install possible, I always try to download directly to the system where I plan to install. MongoDB supports SSL, but their binary distributions don't come with SSL enabled. Here on the server, we can see that our download is complete. On Windows, there's only a manual installation process. The remainder of this video walks through that manual installation process. The Windows download of MongoDB comes as an MSI installer. This can be misleading since most MSI installers also perform the steps necessary to register a service and set up other parts of an application. In the case of MongoDB, all the MSI does is unzip the binaries into a folder. So we click Run on the file that we downloaded. Choose Next. Accept the terms. Click Next. Choose Typical and Install. Even after these unzip, we still have some manual setup to do. Right. When it's done, we click Finish. And we'll use Windows Explorer to see that the files have been installed in Program Files, MongoDB 2.6 Standard, bin. So this is the path to where our binaries are. Note that no special privileges are required to run MongoDB. Before we can run MongoDB, we need to create paths where MongoDB can store logs and data files. We'll do that using the PowerShell. But you could also just use Windows Explorer. First, we create the Mongo directory, and then we create the Mongo data and Mongo logs directories. Using Windows Explorer, we can confirm that the directories have been created the way we expect. A configuration file is necessary to provide the MongoDB process with the path to the logs and data directories. MongoDB configuration files conform to YAML. Since we put our logs and data in the cmongo directory, that's a convenient place to create a configuration file. And this can be a plain text file. We'll call it Mongo CFG. And when we hit Enter, you may see that it's asking you if you really want to change the file extension. Choose Yes. And this can be edited with Notepad. There are many options you can include in your configuration file. For now, the most important are the paths to the logs and data directories. On Windows, we also provide details about the Windows service. In a later video, you'll see how that impacts the creation of a Windows service. We can save and close the configuration file. We're now ready to start the MongoDB server process and identify the config file that it should use. We do that in a PowerShell window. The command simply calls MongoDB and uses the --config to identify our configuration file. We now have a MongoDB process running on our Windows server. We'll leave MongoDB running in this PowerShell window and open up the Processes tab in Task Manager to verify that it started up as we expect. We do that by right-clicking on the start bar and clicking Task Manager. And then go to Processes. And for ease, you may want to sort by name by clicking the name field. And we can see the MongoDB process running. We can also navigate to the logs directory and view our log files using a tool such as Beartail. If there were any errors on startup, they would print out here. This shows that there is a currently running process and that there were no errors. If everything looks good in the logs and from a process standpoint, it's easy to connect to the locally running instance of MongoDB. To do that, we open a PowerShell window and call Program Files, MongoDB, bin, Mongo. Since we didn't change any of the default paths, ports, or other connection details, and we're on localhost, it's not necessary to provide any detail to Mongo. Now we're successfully connected. In this manual install, we've skipped a number of details that will be important for production deployments. Installation of MongoDB on Windows is always a manual process. For production deployments, it's important to isolate the processes and manage the permissions of the files in order to keep the system secure and stable. It's also important that you pay close attention to the size of the log files and rotate them as necessary to prevent log files from consuming 100% of available disk. In this video, we have identified our Windows operating system and that it was 64 bits. We installed MongoDB using a manual process. We also learned 3 ways to verify that the MongoDB process is running: by viewing processes in Task Manager, viewing the logs, and establishing a connection. In the next video, we'll look at integrating the MongoDB service so that it automatically starts when the system boots. In this video, we will ensure that the MongoDB process is configured to start automatically when the system boots. We want to do this so that the MongoDB service is available after system reboots and unexpected system failures. When the system comes back up, the MongoDB process will come back up with it. You might remember that the package installation method on Linux automatically integrated the MongoDB process with the operating system. In this video, we will verify that it is set to start with the expected run level. Windows takes a little more work, but it's straightforward to configure it. Finally, we'll trigger a reboot and make sure that the process is still running when the system comes back up. On Linux, the MongoDB configuration file is in etc init mongodb.conf. In order to confirm the run levels in Linux, we can grep the file for the term run level. This shows that MongoDB will start with run levels 2, 3, 4, and 5. This confirms that MongoDB will start on system boot. Now we'll transition over to the Windows server and configure MongoDB as a Windows service. Let's start by cleaning up some of these windows. And for the currently running MongoDB process, use Control-C. Before we install, let's open up the Windows Service Manager. We can do that by using the Windows search feature. Move your mouse to the top right of the screen, and in the Charms bar, click Search. From Search, type in Services, and select the Services option from the alternatives that are presented. By default, all registered system services are listed in alphabetical order. As we scroll down to the M's, we see that MongoDB is not currently installed. Let's open up the MongoDB configuration file using Windows Explorer. We go to C, Mongo, and open up mongo.cfg. We already know the paths are correct because we ran the MongoDB process in the installation video. The Windows service values look correct. These are what we'll expect to see when we install the service. We need to run a command in PowerShell to perform the installation. In fact, the installation command looks almost identical to the command we used to start the MongoDB process. We simply run the same command, add -- install. Now that MongoDB is installed, it can be managed using the net command. For example, we can start the process using net start MongoDB. Notice that the service name we use is the same that we provided in the Mongo configuration file. Now if we go back to the Windows Service Manager and click Refresh, we now see that MongoDB is installed and running. If we double-click on the service or right-click and choose Properties, we see there are additional options to manage the service. We're most interested in the startup type, which is set to automatic. This means that MongoDB will be started automatically whenever the server boots. We're all set now to do our reboot tests. We'll start with Linux. We have a couple of options to trigger a restart. In Ubuntu, we'll simply use reboot. After issuing the command, we can see that it severed the connection with our PuTTY terminal window on shutdown. We'll give it just a minute and then reconnect. The easiest way to reconnect is in PuTTY to just restart the session. First, we can search the processes, grepping for Mongo. And we see that the process did come up. It now has a process ID of 836. And we can also use the command line client to connect to the server. Everything appears to be working as expected. Now we know that MongoDB will start automatically when the Linux server reboots. Now let's go back to the Windows server. Start by closing out some of these windows. And then by moving our mouse to the top right, we open the Charms bar, click Settings, click Power, and Restart. Other Unplanned will be sufficient for this. Other Unplanned is a good choice. As the server rebooted, it disconnected us from our remote session. After a minute, we can reconnect to verify that MongoDB came back up. We're now reconnected to Windows. First, we'll open up the Windows services by opening the Charms bar and searching for Services, clicking the Services option. When we scroll down to the M's, we see that MongoDB is running. We can open a PowerShell window and establish a connection using the Mongo client, and we're successfully connected. In this video, we have confirmed that the package installation method for Linux properly integrated the MongoDB service to start automatically when the server booted up. We then installed the MongoDB service on Windows and verified that it would automatically start. Finally, we rebooted each server to confirm that MongoDB did actually start automatically. In the next video, we'll learn more about interacting with MongoDB by way of the command line. Now that we have the MongoDB server component set up and running, we need to start using it to store and manage our data. In this video, we will explore using the built-in command line client to work with data. First, we'll make sure that we can run the MongoDB command line client and that its location is present in the path on both Windows and Linux. We'll then move on to make a connection, including specifying the host and port for connections to servers that may not be following typical MongoDB conventions. We'll then explore how to get help on the command line, show server details, and manage and format data. On Linux, the package install places the Mongo executable in a directory that is already in the path. We can confirm that it is on the path by using the tab complete to type out the command. If we want to better understand where it is and how it is on the path, we can run the command which mongo. This shows us that user bin mongo is the location of the Mongo command. We can also view the current path using env and grep for path. And we do see that user bin is in the path. Now we'll have a look at Windows. You may remember that on Windows, the binaries were installed in C program files MongoDB 2.6 standard bin. When we open up a PowerShell, we see that simply typing Mongo doesn't find the application. We have a couple of options to get this on the Windows path, and both can be done by right-clicking on My Computer And both can be done by opening Windows Explorer, right-clicking on this PC or my computer, and choosing Properties. From Properties, we choose Advanced System Settings, and in the Advanced tab of System Properties, we click Environment Variables. In the Environment Variables Management window, you can see that there are user variables and system variables. These scope differences can be important depending on how you manage a particular system. If you want MongoDB binaries to be available to all users on this Windows system, you would modify the path value under System Variables. If you only need the MongoDB binaries to be available to you, then you only need to modify the path value under User Variables. For now, we'll set the path for the current user. We do this by clicking New in the User Variables section, giving it a variable name of path, and then providing the path to the MongoDB binaries. To make this easy, we go over to Windows Explorer and navigate to C, Program Files, MongoDB 2.6 Standard, and Bin. We then click in the address bar, which selects this path, and we can right-click on that and choose Copy. Now we're ready to come back over to the new user variable and paste in that path value. To finish setting this variable, we click OK. We see now that that's in our environment variables for this user. We click OK again, and OK one last time. Unfortunately, any open consoles in Windows may need to be restarted before the change is available to them. So let's open a fresh PowerShell and type Mongo. Now Windows knows where the binary files are, and it runs the MongoDB command line client, successfully connecting us to MongoDB. Up to this point, we have been including both Windows and Linux for each activity. Starting now, there is no difference between how MongoDB works on Windows or Linux. As a result, the remainder of this training, with the exception of the next video about graphical user interfaces, will be done using a Linux server and a command line client. There are two ways to get quick help on the command line options. One is to run the Mongo executable with the -h option. This shows help for that Mongo client. This also works identically on Windows and Linux. If you're on Linux, you can get additional details by using the man page, typing man mongo. For now, we want to focus on the --host and --port commands, arguments. These allow us to specify exactly where we want to connect. Another useful command is the --version command if you need to confirm the version of MongoDB you think you're running. Since we're running locally and are connecting on the default port of 27017, we can build a Mongo connection string that identifies the host as localhost and the port as 27017. Notice that this connects us just as it did before. Now that we're connected, we can get additional help about what commands work on the command line itself by typing help. In particular, there is information about how to use command line client to learn more about the data and find details about MongoDB functions. One useful command is db.serverStatus, which outputs various details for the server. You can see that there's a lot of detail, so it can help to know what you're looking for before you run the command. Inserting data is easy with MongoDB. There's no schema or other prerequisites, so you can just insert any JSON document you like. For example, if we wanted to insert a record that contained our names and interests, we could first run the command use my interests to select a database, followed by db.interests.insert and providing a JSON document. This document, we include a name and a list stored under interests. It is also easy to query data in MongoDB. For example, to get the data back out that we just put in, we could use the command db.interests.find. This will pull back all documents in the interests collection. In this case, there's only one. As documents increase in complexity, it is helpful to format them to be easier to read. We can add .pretty to the previous command to make the output look more human readable. By pressing the up arrow in the command line client, that gives us the last command we ran, and we just add pretty. You can see that this provided indentation and other formatting so that that document was easier to read. Adding pretty to the previous command is called chaining and makes it easy to operate on the output from previous steps. In this video, we have added the MongoDB binaries to the path in Windows and confirmed they are available in the path on Linux. We then connected to our running MongoDB server and discovered how to use the command line client. In the next video, we will look at some of the MongoDB GUIs available for managing data in MongoDB. In this video, we're going to look at a graphical user interface. While the command line client is powerful and standard across all platforms, some people feel more comfortable with a graphical interface. For that reason, we'll take a look at what's available. We're going to start by looking at some of what is available. There are two primary types of GUI, native application and web-based. We'll choose one GUI and install it to get a feel for how they work. Finally, we'll run some of the queries that we did in the command line video. We'll start with the MongoDB website on their docs system under Administration Interfaces. This lists out dozens of alternatives, including links to the websites where you can download it. There are notes and occasional screenshots showing what the requirements are to use each tool. We'll focus on the MongoView interface, which is a .NET GUI that will run on Windows. It's important to understand that many of the tools, especially the higher quality tools, are not free and open source. When we go to the MongoView website, we see that MongoView does have a free usage tier that will support up to 2 connections and 3 views. This may be plenty to get you started, and it will work for our example. We'll follow the downloads link and download the latest binary, saving this to our computer. Depending on your system configuration, you may need to install a different version of .NET. The installer will prompt you if any dependencies are missing. So now we click Open, and inside the zip file that downloaded from MongoView is an MSI installer, which we double-click. We choose Next, and I leave everything default, and you can choose whether or not you want it to install for everyone or just you. Next, and Next to install. We can now close the installer window and open the GUI using a shortcut from the Start menu, MongoView. For now, we'll click OK to continue using the free edition. To establish a connection, we click on File and Connect. And in the Connect dialog, we can click the green plus to add a new connection. We'll call this Local Connection. The server we're connecting to is localhost with the default port. And we can leave username, password, and database empty since we're not using authentication. There's a test button which allows us to verify that these credentials are correct, and you get a success message. I can now save this connection and click the Connect button. Once the connection is made, the GUI fetches some information about the databases and collections that are available on the server. If you ever think that changes have occurred since you began looking at the database, you can click Refresh to synchronize it with the current state of the MongoDB database. Here we see each database, and for each database we see options to view collections, stored JavaScript, and gridfs details. Let's create the My Interests database by right-clicking on Local Connection and choosing Add Database. We then type in the name of the database and click OK. Then we can right-click on the My Interests database and add a collection, which we'll call. To add a new record, we can right-click on the collection and choose Insert Import, which allows us, from the dialog that shows up, we can either type in a single JSON document or multiple documents from a text file. In this case, we're going to For this example, we'll use the same JSON document we inserted in the command line. And then we click Insert, which will generate the actual call sent to MongoDB and insert the data. If we want to view data in this database, an easy way to view data in this collection is to double-click on the interests collection. Notice there are several tabs here. There's a text view, which shows us the raw results the way we would see them on the command line if we had run this same query. It also attempts to create a tabular view of the data. In this case, it shows that interests contains an array of 2, which when we hover over that field, it shows us the 2 values in that list, or array. The tree view is somewhat like the pretty output, which shows hierarchically the relationship between different values in the JSON document. If we want to be more specific, we also have the option of right-clicking and choosing Find, or clicking on the collection of interest and clicking Find from the menu. Here we have an option to add criteria and selectively limit what MongoDB returns back. And we'll cover querying in more detail in a later video. In this video, we browsed the available graphical administration tools for MongoDB on the official website. We then chose MongoView, which we installed natively on Windows. We established a connection between the GUI and our MongoDB server that is running locally, and learned how to view, add, and manage data. This brings us to the end of the Getting Started section. In this section, we successfully identified and downloaded the appropriate version of MongoDB for our desired system. We did this on both Windows and Linux. We then configured MongoDB so that it would start automatically on system boot. Finally, we demonstrated how to interface with MongoDB in a few different ways, including the command line client and the GUI client. In the next section, we will learn more about JSON and data operations in MongoDB. In this section, we begin to explore JSON and data operations. We'll begin with an overview of JSON, which stands for JavaScript Object Notation. We then review the structured but schemaless nature of MongoDB. With that foundation, we then get familiar with the mechanics of adding and querying, including some advanced query constructs such as sort, limit, and projections. In this video, we start with an overview of JavaScript Object Notation, known as JSON. Resources used in this video include the main JSON website, json.org, a text editor, and an online JSON parser that is very useful in examining and crafting JSON objects. We also learn about BSON, which is binary JSON, including some of the data formats in MongoDB that leverage this binary format. We'll also discover that JSON has broad programming language support. json.org is the official website for JSON. JSON is a data interchange format, not a programming language. Unlike XML, JSON is lightweight and fast to process. It is also more compact than XML, which reduces overall network strain. JSON is also easy for humans to read and has a refreshingly simple definition. In fact, the entire definition is contained in the 5 images below. JSON is built on 2 building blocks, a collection of name-value pairs. An object begins and closes with curly braces. Name-value pairs exist on each side of a colon, with the name always on the left. Multiple name-value pairs are separated by commas. Names are always strings. An array is an ordered list of values, separated by commas and contained inside square brackets. A value can be a string, a number, and even another object, also called an embedded object, an array, a Boolean value, or null. Strings are contained within quotes and can include any Unicode character, including a number of special characters that require escaping. A number can take any form, including exponential notation and floating point precision. Now we'll look at a few example JSON documents. In this first example, you'll see that we have 5 name-value pairs. The names, which you can think of as keys, are name, email, major, test scores, and course GPAs. The values include 1 embedded object with 2 name-value pairs, and 2 strings, and 2 arrays. Notice that JSON can be represented easily in plain text, just like XML. Let's copy this object, and we can use an online JSON parser to more closely examine the object. The instructor object is a little more interesting, so let's copy this and paste it into our online JSON parser. Here we also have an embedded object, and now we have two array values. Let's add some course numbers to the course values. You'll notice that as the parser finds errors, it highlights them. This is very fast and makes it effortless to craft objects that represent valid JSON. The same element that allowed us to enable beautification of JSON documents will also enable us to show types and indexes. As you can see here, the array is shown as zero-based, even though JSON doesn't define a direct access mechanism. That may be different. The indexing of array elements may be different depending on the specific language drivers you're using and the data type used to map arrays. This view also makes it obvious to see embedded objects and other data types. Now let's learn a little bit more about bson on mongodb.org. bson is an extension of JSON which adds some specialized types and accommodates some performance enhancements and space efficiencies within the MongoDB engine. Notice that there are many more binary data types than there were JSON types. This is to accommodate storage and query of common types, such as date and object IDs. Here in our text editor, we have a sample bson document which includes a MongoDB-generated object ID. When we copy this into the JSON parser, we quickly see that MongoDB's representation of an object ID does not conform to standard JSON. This is important because it reminds us that in order to manage bson documents suitable for MongoDB requires a MongoDB library or client. Up to this point, I have referred to JSON objects. MongoDB refers to them as documents. Throughout these videos, you may hear me use the terms object and document interchangeably. They refer to the same thing, a JSON object. For now, we'll clear out the object ID and make an important observation that MongoDB doesn't care about quotes. For example, if I change the email to show without quotes, the JSON parser complains that it is invalid. However, MongoDB would interpret email as a valid name for the value john.shore@gmail.com. Back on the json.org website, it's helpful to notice that JSON enjoys broad programming language support. These include popular languages like Python, C#, Java, and Objective-C. It also includes more special purpose languages such as Erlang, R, and LotusScript. In this video, we explored JSON by using a text editor and an online JSON parser. We also learned that libraries have been created for many programming languages to support the use of JSON. In the next video, we'll look at what schema and structure mean in MongoDB. In this video, we'll review the roles of schema and structure in MongoDB. We'll look at these concepts by comparing MongoDB to relational databases. We'll then map concepts from relational database tables onto MongoDB collections. In particular, the ability of a collection to hold disparate types. Finally, we'll explore the idea of implicit schema, or how applications impose a type of schema on the data that is stored in MongoDB. We'll be looking at an example from a code camp where I presented on MongoDB. In this example, we consider a course tracking system that needs to accommodate students, instructors, and courses, as well as some related details about the instructors. In a relational database, this could be represented as the tables shown here. A relational database has a rigid schema, where all data and interrelationships must be defined ahead of time. A key principle in relational design is normalization, which splits data into components to decrease duplication and identify entities. The same data in MongoDB could be represented as shown here. Notice that there are no relationships drawn. This is because in MongoDB there is no such thing as an enforceable foreign key relationship. You can see that the courses and publications tables have been consumed by the instructor object. Let's work some code here to get a better feel for how these changes are represented. We'll start by connecting to a MySQL database and creating a table in MySQL which represents a student. We first have to create a database and then use that database, at which point we're free to create the table. We can then insert a record and issue a simple select to verify that the record was inserted as we expected. So let's leave up MySQL here and start a new session where we can connect to Mongo. Unlike the relational database, we don't need to create the database. When we issue the use database command, the database doesn't need to exist. It will be created implicitly when we add the first document. So in spite of the fact that we just got a message that we switched to DB course tracker, if we show DBs, you'll see that course tracker still doesn't exist because we haven't added a record to it. We can insert a document and implicitly create the collection as shown here. Just to recap, the database, course tracker, and the collection student were lazily instantiated when we inserted the first document. To illustrate the effect of a rigid schema, let's go back to the relational database and attempt to insert a record that includes additional information. For example, let's add a value representing his GPA. You can see that the relational database notifies us of an error, that the column GPA doesn't exist, that the column GPA is unknown. On the other hand, in MongoDB, we can easily add the modified document to the existing collection. In fact, we can add a document that looks completely different, and MongoDB will simply store the document in the collection for us. Whereas a table in a relational database has predefined fields and structure, a collection in MongoDB has none. The collection will hold any document it is given, regardless of its structure. While it's true that MongoDB does not impose a schema on your use of collections, there is typically an implicit schema represented by the types in your application. In other words, the schema now exists in application code. Let's have a quick look at an example using the Python programming language. Applications often define types, whether they are Java classes, Python dictionaries, or structs in C. These types represent a schema. When you store one of these types in MongoDB or reconstitute an in-memory representation of it from MongoDB, your application code is expecting certain values. In this Python class, we see a new student object is expecting a name attribute, which is a Python dictionary, and 2 string attributes for email and major. This means that any document in MongoDB that will be used to create a new student object must have values for each of the 4 parameters that are passed into the constructor to populate those 3 class attributes. This also implies that any document which contains more data than the required values can't be fully represented as an instance of this class. In the main function, I show how to create a student instance and save that instance to MongoDB, which requires conversion to JSON. I then query MongoDB for the document and output the result. Finally, I create a new instance of student using the values that came from MongoDB and output the first name. Since MongoDB does not enforce the structure of a given type by way of a schema, your application code needs to be able to handle cases where data coming in may not align perfectly with a defined type. For example, if you attempt to access a key that doesn't exist in the document returned by MongoDB, it will throw a key error. Your application must be able to handle this. In this video, we compared relational structure to document structure in MongoDB. We then demonstrated some of the key differences between tables and collections. Tables hold one type of thing, and all things in a table must be the same type. A collection can hold a variety of things. Finally, we discovered that applications represent a type of implicit schema. In the next video, we'll explore various ways to add data to MongoDB. In this video, we explore various ways to add data to MongoDB. We'll start with basic document inserts. We'll then learn how to update existing documents, including MongoDB special operations, such as increment and push onto a list. Finally, we'll review the object ID in MongoDB and why it's relevant for you. Putting data into MongoDB is very simple. You start by identifying the database you want to use with the use command. After issuing the use command, the database is referred to as DB. All documents must go in collections. You specify the collection by calling db.collectionName. In this case, we see db.student. For the student collection, we use db.student. It is then possible to call insert on that collection with db.student.insert. Let's select this insert statement and run it in MongoDB. This all comes together in this insert command for a student document. Copy this and run it in the Mongo shell. After inserting the document, we can call find to retrieve it. You see that when you insert an ID, if you don't include a key name of _ID in the document, MongoDB assigns an object ID for you. We'll learn more about object IDs in a minute. Let's add a few more documents. Instructor and find commands help us confirm that they were inserted correctly. At this point, we have inserted 3 documents in 3 different collections. You can see that the instructor includes empty arrays for publications and courses, and that the course document has an empty array for evaluations. We can easily see how much space a collection is using on disk with the command db.collectionname.stats and providing it a scale. The scale argument makes it possible to show the resulting values in any scale desired. For example, a scale of 1024 will show all values in kilobytes. Now that we have data in MongoDB, we may want to add to that data or change the data that we have in there. For example, we may want to increment the number of students in a course, or add a new publication to the instructor's list of publications. We can see on mongodb.org that these are accomplished by way of update operators. Let's call find on course to get a plain representation of the document. We can easily copy this into the online parser tool and see the empty array for evaluations. For now, we'll get rid of the object ID. Let's see how it would look to add a new evaluation. We can copy this evaluation and craft a query in MongoDB that will update the existing document with the new evaluation. We do this by identifying the database using db, followed by the collection name and the command update. The first argument is the query example. The next argument is the update that we would like to happen. Here we indicate that we would like to push a value onto the evaluations and paste in the JSON document where we crafted the online parser. Here we indicate that we would like to push a value onto evaluations. And we've pasted the JSON object that we crafted in the online parser. Notice we get the message back that one document was matched and one document was modified. When we query for the document, we can see that it was updated as expected and the array now contains the evaluation. Incrementing the number of students is similar, except that this time we use the inc command and provide a number by which to increment the identified field. We can now query for this document and see that it is updated. Let's take a closer look at the object ID. Object ID values in MongoDB are automatically assigned in cases where a document that is inserted does not include one. They must be unique. The generated object ID values contain a lot of additional information that is used by MongoDB. On the MongoDB website, we can read about the composition of an object ID. Notice that the first 4 bytes are a timestamp. These are followed by a 3-byte machine identifier, a 2-byte process ID, and finally a 3-byte counter that increments with each new record. It may be useful to have a creation time of a document, which is available by default when you use MongoDB object ID values. This can be easier to visualize when looking at the API description. In this video, we have learned how to insert documents as well as add data to and modify data in existing documents. We also reviewed the composition of automatically generated MongoDB object IDs. In the next video, we'll learn more about how to query data in MongoDB. In this video, we will explore ways to query MongoDB to find data. MongoDB uses a query by example mechanism. After learning how to use query by example, we cover limits, iteration, and finally discuss indexing for performance. In the previous video, we added a few documents for student, instructor, and course. We're going to add some documents to the student collection in order to make our examples in this video more realistic. MongoDB accommodates a bulk insert by providing the insert function call a list of documents instead of a single document. For convenience, we put this command in a separate JavaScript file and call it from the command line by calling the Mongo client and providing the arguments of database and JavaScript file. We can now connect to Mongo and verify the documents were inserted into the database by first using the database and then issuing a call to the student collection to return a count. We see that there are 32 documents in the collection, which means our import was successful. Often the number of records returned by MongoDB for a query would not fit on a single screen. By default, MongoDB will only show the first 20 documents. For example, if I call db.student.find, it returns only the first 20 documents. It is possible to iterate through the remaining documents by using the it command as indicated at the end of the results output. You can see that when we reach the last document matching the query, the iteration message no longer prints out. You may limit the number of results that come back by chaining the limit command onto any query. In this case, even though there may be more records that match the given query, only 4 will be returned. Sorting data is also possible in MongoDB by chaining the sort function. In this example, we are telling MongoDB to sort matching documents based on the contents of the first name field in descending order. And so we see in the results that we start with Zachary and then go on to Wendell, Wade, and Virginia. Sort order can be changed by removing the negative sign from the 1, in which case we now have results in ascending order, starting with Angel, April, and Barbara. Now let's dig into the query semantics in MongoDB. We'll start by considering that in a relational database, the structure of each record is known at query time. This makes it possible to create queries based on known fields and data types. Since MongoDB databases don't have schemas, it's not possible to query based on specific fields or data types. After all, every document in a collection may not share any structural similarities with other documents in the same collection. To find documents in MongoDB, we create a new JSON object and tell MongoDB to find all the documents that look similar. This is called query by example, since we give MongoDB an example of what we want to find and ask it to look for other documents that are similar. For our first example document, let's start with a full document and work backward. First, we copy a full student record into the online parser. We can remove the object ID, which leaves us with the 3 original name-value pairs. If we want to search based on email, we can remove the other name-value pairs from the JSON document. The absence of a name in an example document means that any value, or the absence of a value, can be considered as a match. We're left with a simple JSON object that has a single name-value pair. And note that we can change the email shown here to any email we like. When we build this into a query in MongoDB, we are telling MongoDB to search all documents in the collection and return any document that has a name of email with a corresponding value of lee2331@aol.com. In other words, a document must have a property with the name email, and a value for that property must match the given email. In this case, only one result matched. It can be more obvious to see the match if we run it with pretty. Let me scroll back up to see that, in fact, the email does match our query criteria. It's easy to query for embedded objects too. In this case, we use a notation that looks like chaining in the name field. This is called dot notation. This example JSON object says to look for any document that has a name of name with an embedded object with a name of first and a value equal to Jeff. We can see that we got one result back. It is possible to query embedded documents by example without using the dot notation, but an exact match is required. Consider the example where we query for just the name field using an embedded document. Notice that no results are found. However, if we match the embedded document exactly, we get our match. The dot notation is more flexible for querying embedded documents. Indexing is a powerful tool to improve performance. An index can be created on any collection using index with a JSON object indicating the property name on which the index should be created. Indexes are designed to speed up access time to data. However, they can also decrease the speed of inserting data since MongoDB has to do more work. First, it inserts the document, and then it updates any affected index. Before creating an index in a production environment, be sure to test the impact of writes as well as reads. After running the ensure index command, we get an output that indicates there was one index before and there are now 2 indexes. We can view indexes on a collection by calling the getIndexes command on that collection. We can also view indexes for the entire system using this command. In this video, we learned how to query by example. We also learned how to iterate through results, limit the number of results returned, and sort results. Finally, we learned how to create an index and consider the total impact of creating indexes. In the next video, we'll consider some advanced query strategies in MongoDB. In this video, we explore some advanced query capabilities in MongoDB. We'll learn how to use regular expressions for full text search. We'll then learn about projections for more sophisticated querying of array elements. Finally, we learn how to limit which fields are returned with query results. A regular expression is a text pattern matching tool. Regular expressions can match exact text or patterns that include variable amounts of space or classes of characters. Regular expressions are run using the operator regex. If we wanted to find all documents in the student collection where the first name contains en, we could do that with this expression. Whenever we log in fresh to MongoDB, we need to make sure we use the correct database. Notice that this returns Darlene, Wendell, and any other document where the first name contains the characters en. Regular expressions also contain special characters that identify positional matches. The caret, for example, indicates the start of a line. So the regular expression caret j, as shown here, will search for any value that starts with a lowercase j. You'll notice that this query didn't return any results, despite the fact that there are several first names that start with j. That's because by default, all regular expressions are case sensitive. Options can be passed to a regular expression call that tell it to process differently. An example would be the case insensitive flag I. When we run this, we now see results come back. We could have also done a case sensitive search and used a capital J. Since regular expressions are so useful and powerful, MongoDB includes a shorthand to use them. You can simply surround your regular expression by forward slashes. Any options follow the closing forward slash. In this example, we're looking for any first name that contains DA regardless of case, or where they occur in the value. And here we got back Darlene because it starts with DA and our query was case insensitive. It's easy to limit the fields that display in the result set. This requires a JSON object that tells MongoDB what to return, similar to how we query by example. For example, let's imagine that we only care about viewing the email address in a result set. We can do that by adding a JSON object as the second argument to the call we make to the find function, like this. The 1 indicates that the field should be included. You'll notice that the _ID field is returned even though we didn't explicitly ask for it. If you want to conceal the ID value, it's necessary to omit it explicitly. We can do that with this command. Projections allow us to slice and match against list values. For example, let's say that we only wanted to see the last 5 values from a student's individual course GPAs. We can use this query to tell MongoDB to slice the course GPA's value, returning only the last 5. You can see now that each result that comes back only contains the last 5 course GPAs. If we had provided a positive 5, it would have returned the first 5 GPAs. We can also return a fixed number of values from the array using the notation of starting, offset, and number to return. For example, this query returns 8 elements starting at element 10. Notice that not all records include 8 values. That's because some of them have fewer than 18 elements in total. The other projection allows matching and comparison operators on values in an array. Imagine that we wanted to view students whose test scores were 650 or higher. We could do that with this query. Notice that we're able to use the greater than operator. We can even chain a sort to this so that we get the highest score first, then the rest in descending order. It may not be obvious, but this query would match both tests. For example, if we lowered the value to 10, then it shows ACT scores. We can be more specific by modifying it to specify the test too. Here we're saying that we want to match both the test equals SAT and score greater than 650. In this video, we have learned how to use regular expressions to query MongoDB. We also learned how to limit which fields are included in a result set and how projections work to return specific elements in array properties. In this section, we had an overview of JSON and learned that MongoDB is schemaless, but does have structure. We also learned about the application-imposed schema in MongoDB. We learned how to add data to and query data from MongoDB, including how to create an index. Finally, we reviewed some advanced query capabilities in MongoDB. In the next section, we'll dive into working with databases in MongoDB. In this section, we'll be learning how to work with databases in MongoDB. This includes pruning data from existing databases and collections. We'll go over backup and restore of a database and review some additional backup options. Finally, we'll review security practices in MongoDB, including how the file system, CPU, memory, and network all factor into securing your MongoDB instance. In this video, we'll cover pruning data from database collections. In particular, we'll discover the selection criteria to ensure that we remove only targeted data. We'll learn how to drop entire collections and databases. We'll also learn how to drop entire collections and databases. We'll start by importing some data. For this, we use the same JavaScript file import method we used in previous videos. To do this, we call Mongo, identify the database name, and highlight the JavaScript file that contains the documents we want to import. We can then log into Mongo and confirm that the records were imported by getting a count of existing records. We do this by first using the database and then calling count on the student collection. We see 29 records, so we're all set. In a previous video, we learned how to query data in MongoDB. Before I remove data from MongoDB, I always start with a basic query. This makes it possible to verify that I will only remove the data I'm interested in removing. In this case, I want to remove the student record with a first name of Wendell. Based on the results of the query, I can see that my remove command would only remove one record. If from the output it's not obvious that there's only one record that's been selected, you can always change the output to count, which verifies that only one record meets this criteria. To remove the record, all we need to do is change the find to remove. As long as I leave everything else exactly as it was in the query, I can be confident that it will only affect one record. We can see in the output that one record was removed. We can further verify that only one record was removed by getting a count of existing records. Here we see that there are 28 records where we started with 29, so that looks good. We can even go one step further and run our original query. Since we think we removed it, we would expect to see no results come back. That is the case. We removed Wendell's record from MongoDB. As you can see, remove uses query by example, just like find. So it follows that an empty example document will return all documents. Since we know that an empty example document will return all documents, it follows that calling remove with an empty document example would match all documents and effectively remove all documents from a collection, although it would leave an empty collection. We can see that the remove command uses query by example, just like find. Since we also know that an empty example document returns all documents, it follows that calling remove with an empty example document would match all documents and effectively remove all documents from a collection, although it would leave an empty collection. Here we can see that it removed 28 records, and when we run count on the student collection, we see that there are 0 records left. We can see all available collections using the show collections command in MongoDB. In the case that we want to remove an entire collection, there is a command to drop a collection. In this case, we would call db.student.drop, which will drop the entire collection. When we run show collections again, we see that the student collection no longer exists. Similarly, we can drop an entire database. First, let's see what databases are present using the show dbs command. Now, if we call db.dropDatabase, we can remove the database and all collections that it contains. We see from the response that it has dropped the database. We can confirm this by calling show dbs again. Note that all remove and drop commands are final and permanent. There is no undo command. This is one reason it's important to have a good backup and restore process, which we'll cover in a later video. In this video, we learned how to remove using query by example to identify the records we want to remove. We also learned how to drop entire collections and even databases. All remove and drop actions are permanent and data cannot be restored. In the next video, we'll learn how to back up a MongoDB database. In this video, we learn how to back up a MongoDB database. MongoDB includes a MongoDump utility which creates a snapshot of a database. MongoDumps can span multiple MongoDB versions with some restrictions. Dumps can be focused or broad, to include individual databases or include many databases. The MongoDump format changed in version 2.2. On the MongoDB website, we see that the MongoDump format changed in version 2.2, making dumps prior to version 2.2 incompatible with later versions of MongoDB. Fortunately, MongoDB 2.2 was released 2 years ago and newer installations are likely to use a later version, so version compatibility is greatly increased. MongoDump creates a collection of files that represent the collections in your database. These files are in a binary format representing MongoDB's internal BSON format. Let's start by importing our sample data. It's easy to run MongoDump. We need to identify a directory where we want dump files to be stored. In this case, we'll use opt backup MongoDump. In the call to MongoDump, we also identify the database we want to back up with the --db argument. From the output, we see that we backed up 29 records from the student collection. We can change into the dump directory and view the dump files that we created. You can see that the first structural element within the MongoDump directory is a directory with the name of the database, so that all collection information for that database are contained within that directory. Within the database directory, we see files that correspond to the collections themselves, as well as system indexes. Even though the dump file is binary, we can see some of the details in a text editor. For example, if we vi into MongoDump course tracker student bson, we can see certain bits of text like jeff@yahoo.com, business, test scores, and so on. However, most of the details are in an unreadable binary format. We now have a successful dump of our database. It's possible to keep track of different database backups in an efficient way using a revision control tool. On Linux, Git is a convenient choice. By tracking backup revisions, we can restore data at a point in time. On Linux, Git can easily be installed using existing packages. For example, on Ubuntu 14.04 LTS, we install Git with this command. In order to commit changes into Git repositories, we need to provide Git with some configuration details. At a minimum, we provide email and name values. These will be associated with each commit. Git does not require a central server. This makes it possible to create a local repository by calling git init when inside the MongoDump directory. At this point, we can add files to the initialized repository using git add star. Now we're ready to commit this revision, which we do with the git commit command, and provide a message for the commit. We can confirm that our commit worked with the git log command. We have effectively backed up and created a permanent revision of that backup using git. We can now log back into MongoDB and make some changes to our database. Let's change Desiree's name. We can now log back into MongoDB and make some changes to our database. We start by using Course Tracker, after which we can make changes. Let's change Desiree's name and Bridget's email and update various details about April, including test and name, and finally change Mandy's major. Imagine now that we wanted to create a new dump to capture these changes that were made. To do this, we exit out of MongoDB and run the MongoDump command. We use exactly the same command, which will overwrite existing dump files. Since we already have that dump captured in Git, we can confidently overwrite the same files. From the MongoDump directory, we can ask for get the status, which shows the student.bson file changed. Since the files are binary, it's difficult to compare the previous version to this one directly. However, we can see some details in a text editor. We trust that MongoDump is working as expected. In order to commit this new dump, we use the same commit command we used earlier with the -a argument added, and obviously we provide a different message. Now when we run git log, we see 2 revisions committed. We can easily restore the previous dump revision if we ever needed the data exactly as it existed then. In this video, we learned that MongoDump creates a snapshot of a database as it exists now. This can be done while the database is running without interrupting normal operations. Since version 2.2, MongoDump output is version independent, making it possible to upgrade to a newer version of MongoDB with confidence that old dumps can still be restored. In the next video, we will discover how to restore a database. In this video, we will learn how to restore a database using an existing MongoDump. Specifically, we'll learn how to identify the correct backup. We'll then use MongoRestore to perform the restore and verify the database. Finally, we'll review some potentially inconsistent restore scenarios. Before we restore, we'll log into Mongo and drop our existing database. We do this by selecting our database and using the db.drop database and using the db.drop database command that we learned about in the pruning video. MongoDB's MongoDump command has a corollary command, MongoRestore. MongoRestore expects a path to existing MongoDump output and takes care of the rest. Details about the database name, indexes, and related system properties are all included in the MongoDump files. MongoRestore uses these to create the database and restore all related data. After restoring a database, we can log in and confirm that the data is back in place. First, we confirm that the database exists by using showDBs. We can then use our database and show collections to verify that the student collection was restored. We see that the student collection exists, and a count on that collection shows 29 records, which is exactly what we expect. The MongoDump that we restored should be the latest version. The expected records should have the latest changes that were made. We can verify this by selecting specific records. We see that Desiree's name is current, and that Bridget's email also reflects the changes that we made. Our data has been restored to the latest MongoDump revision. Let's say we now wanted to restore the data as it existed previously. We can drop the current database and restore from a previous version. We do this by first running db.drop database. Now we exit Mongo and ensure that we're in the opt backup MongoDump directory. Here we can view available backups using git log. Once we identify the specific revision we want to restore, we can use git checkout and provide the hash from the git log output. This updates all files to that specific revision. We're now ready to run MongoRestore on these dump files. At this point, we would expect the database to be restored to its original data. We can now log back into Mongo and confirm that the database exists using showDBs. Next, we use the database and confirm that the collection exists. Finally, we can query for Desiree's name and see that her name appears as it originally did. And naturally we can do the same for Bridget's email, which is back to bridget@msn.com. When MongoDB dumps and restores data using MongoDump and MongoRestore, this includes the object ID values. In fact, MongoRestore uses these values to decide whether or not to restore each document. When a document with an object ID matching the one encountered by MongoRestore is found, MongoDB does not attempt to merge different versions of a document. Instead, that document is skipped. If the object ID is not found in the collection, it is inserted as it exists in the MongoDump output. This is important because existing documents can prevent a restore from happening, which may result in inconsistent data. A good rule of thumb is to always drop data before executing a restore. In this video, we have learned how to restore our MongoDB database to a previous revision using MongoRestore. We have also verified that MongoRestore works and that, when we use get, it is possible to restore specific prior versions. We observed that it is also important to drop existing data before restoring to ensure consistent data after restore. In the next video, we will review additional options to back up MongoDB databases. In this video, we review some additional options to create MongoDB backups. In particular, we will look at replica sets, file system backups, and MMS backups. This video will be less hands-on than other videos for an important reason. These solutions can be much more complicated to set up and may not be a good fit for all use cases of MongoDB. Some of these topics will be covered in more detail in later videos. This diagram illustrates 4 backup or redundancy scenarios. By redundancy, I mean to refer to the case where live distributed replicas ensure that data is always available and eventually consistent. In some cases, it may make sense to use a combination of these approaches to achieve the most reliable system possible. The first scenario is the most traditional route, where the official MongoDump and MongoRestore utilities are used to manage backups and restores for a MongoDB deployment. This will work in all cases, and we've been through the process in the previous videos. If you're not sure where to start, this is a safe, supported mechanism to back up your MongoDB database. In this scenario, you have one Mongo instance running. MongoDB also supports direct file system backups. This approach is more complicated to set up, but it can lead to a more easily automated backup process. In this scenario, the Linux file system is configured to use Logical Volume Manager, or LVM, which makes it possible to take snapshots of the file system without disturbing operations of MongoDB. As you can see on the mongodb.org website, the setup is complicated and requires thought and special expertise ahead of time to set up. Decisions include whether the MongoDB data files will be isolated on their own logical partition, whether or not to use journaling, and what to do with backups to ensure that they survive full system failure. The published method does not provide support for incremental backups. While replica sets are not exactly a backup mechanism, they do provide resilience to system failure. In this scenario, multiple machines are identified as nodes in a replica set. These nodes communicate to identify a master to handle write requests and slaves for read requests. All data is replicated to all nodes. Nodes can span logical servers, physical racks, and even data centers. For systems that require a great deal of reliability, replica sets can prevent downtime, which is often associated with a restore process, since surviving nodes remain live and continue responding to requests even when another node in the set fails. Mongo Monitoring Service, or MMS, is a service offered by Tengen, the company behind MongoDB. This service provides a monitoring service that has an integrated backup. The backups that are created by MMS provide a point-in-time recovery. This option has ongoing cost, but brings some value that may make it worthwhile. We'll review MMS in more detail later in this training. Which options you choose to incorporate into your backup and reliability plan when using MongoDB will depend on budget, available expertise, operating system constraints, and the overall reliability needs of your application. The more demanding your needs are, the more thought you should put into your backup plan. In this video, we reviewed various backup options that are possible when using MongoDB. Many of these represent additional complexity, and some add ongoing cost to your MongoDB deployment. Some of the options considered include replica sets, file system backups, and 10gen's MMS offering. In the next video, we'll discuss security in MongoDB. In this video, we consider security in MongoDB. Securing a database requires paying attention to data as it exists at various layers within your system, from the operating system down through network communications. Encryption is one way to secure data within your database. Here we see that data from your MongoDB database is present in the CPU, RAM, disk, and network at different times during normal operations. In order to properly secure data while in the CPU and RAM requires a well-secured operating system. File systems store all data that is not currently cached in RAM or being processed by the CPU and must be secured. File system management often extends beyond the operating system with solutions such as network-attached storage and shared file systems. Data from MongoDB also frequently travels across network connections, whether it's to synchronize replica sets or return data results. Networks are even further removed from operating system protections as they travel across private and public networks. Operating system level hardening is beyond the scope of this training series. It would be wise to ensure that your deployment environment is set up and monitored by a qualified system administrator. The MongoDB.org website provides many security guidelines to give guidance. Remember that each deployment scenario is likely to present different security requirements depending on the type of environment, such as shared, virtualized, or dedicated. The backups that we created in this section were stored on disk in the directory opt backup MongoDump. You may remember from the installation videos that the MongoDB process is owned by the system user MongoDB. We can confirm this by listing processes and grepping for Mongo. One way to secure the files on disk is to make sure that the backup files are owned by MongoDB. Given the listing above, we see that the files are currently owned by root. This is easy to change using the own command, where the -r executes the change recursively on all subdirectories. We can now verify that the files are owned by MongoDB, even into subdirectories. Linux file permissions are configurable by user, group, and world. The output from this listing shows us that the MongoDump directory and subdirectories and files give the user read, write, and execute permissions. It is also observed that group and world can read and execute files in that directory. These world permissions mean that any user on this system can read the MongoDump files that were created. We can change that with the chmod command, again using the recursive flag and indicating that we want it to be read, write, and execute by the user, readable by group, and completely unavailable to world. If we do another listing, we can see that the files are now only readable by user and group, but that no one else on the system can view them. This is a good start, but the files are still unencrypted, which means that physical loss of the server or a compromised system could still result in exposure of data. Disk encryption is available, but differs from one system to another. MongoDB does not endorse a specific type of encryption, but it does provide integration with certain encryption vendors. In our backup scenarios, we have used a local Git repository to version our backups. If a central Git repository is used to store these backup files, then similar attention will be required to secure the network transmission and Git file system storage. It's wise to seek guidance from network, system, and other engineers to secure specific parts of MongoDB. The more sensitive the data, or costly the breach, the more effort you should give to the security up front. These experts should include system administrators, network administrators, and possibly even third-party tools to provide encryption services. In this section, we have learned how to prune data from MongoDB databases. We have learned how to backup and restore databases using MongoDump and MongoRestore. Additional backup options, including file system backups, replica sets, and MMS, may be appropriate for certain situations. Security is important and may require input from specialists to ensure proper execution. In the next section, we will learn how to use MapReduce to create more sophisticated views into our data. In this section, we'll be exploring the powerful MapReduce capability of MongoDB. We'll begin with an overview of what MapReduce is and how we can use it. We'll then go through the creation of a map and reduce function one at a time. Next, we'll explore some advanced MapReduce techniques before moving on to a discussion of when to use MapReduce. This first video provides an overview of MapReduce. Creating effective MapReduce algorithms requires a solid understanding of the data. The desired end result needs to be defined, and any questions or modifications to existing data should be identified. We'll need a more diverse set of data in order to complete this section. We can import this data just as we have in previous videos. First, we populate a bulk import data file on the server. We place the bulk import data file on the server and call Mongo to import the data. We can then log into Mongo and use Course Tracker and confirm that the collections are available. In keeping with our focus on students in previous sections, we'll be extending the Course Tracker example by adding instructor and course documents. We will also be introducing the idea of document references. You can see that an instructor document will reference courses and that course documents will reference students. Proper understanding of relationships is critical when designing MapReduce algorithms. You may have noticed that our sample data specifies ID values. This is for convenience in referencing so that we don't have to identify automatically generated object IDs. From the Mongo command line, we can query for an instructor document. Notice that the ID is not an object ID, as was already mentioned. We see that there is a courses array which contains references to the ID values found in the course documents. When we query for a course document, we see that there is a students array which contains references to the ID values from documents in the student collection. Finally, we can query for a student document and see that there are no backward references to course or instructor. All references go in one direction. As we learned in Section 2, the documents have been normalized only far enough to prevent significant duplication of data. Now that we understand what the data looks like, let's do a very basic MapReduce to find the number of courses for which each student has signed up. All the data we need is in the courses collection, but it's distributed among all documents. What we want to do is take the data from the students array and reorganize it to be sorted by student ID and represent a sum totaling the number of times the student ID appears in any course. In the Mongo shell, we want to create the map function. The keyword "this" refers to a single course document. So this .students is the array of student ID values. This function loops over those student ID values and emits the value of 1 with a student ID as the key. If this isn't perfectly clear right now, don't worry. We're going to go over this in more detail in the next video. The reduce function catches emitted values by key. It's important to understand that it doesn't catch them one at a time as they are emitted. The reduce function is not called until all emit calls have been made. In this case, we would expect the key coming in to match one of the student ID values. The values variable will be an array containing all the values that were emitted for the given key. In this simple case, these will all be 1s because that's all we emit. This function then loops over that array and obtains a sum. When the reduce function returns that sum, the return value is associated with the key that passed in the array of values. We can run the MapReduce by identifying the DB, collection, and calling MapReduce. This function expects references to the map function, the reduce function, and information about what to do with the result of the MapReduce operation. In this case, we overwrite or create a collection number courses. After we run the MapReduce, we can show collections and see the new collection. When we do a find on that collection, we see the student ID values along with the total number of courses corresponding to each. After we run the MapReduce, various results about what the MapReduce did are displayed. We can also show collections and see the new collection, number courses. When we do a find on that collection, we see the student ID values along with the total number of courses corresponding to each. As we review the diagram again, in this diagram we see that what we did is for each course document we looped through all student ID values. Each student ID value was emitted as a key with a value of 1. All of these emitted values were later collected into an array which was passed to the reduce function to calculate the sum. In this video we learned how important it is to understand the structure of existing data in order to create MapReduce functions. We also discovered that it's important to know ahead of time what the end result should look like and any calculations required to achieve it. In the next video we'll look more closely at creating map functions. In this video we will create a map function. Of particular importance when creating a map function is a clear understanding of the data you want to map and the desired end structure. The glue that holds these together is a common key, which is used to link the map and reduce operations. In this video we'll be working with the same data we imported in video 1 of this section. So we'll use course tracker. If for any reason you have deleted the data, please repeat the import steps from the first video. Let's start off by querying for one course document. In the document we see two arrays, one of which, the students array, contains ID values referencing students. It does not include any other details about the student, such as first and last name or email address. We can likewise query for a student document. Notice there are no references from the student document out to other documents. Each student document contains details such as first and last name and email address. In order to build a course report, we need to look through all course documents and see how many times each student ID appears. We then need to get the first and last name from the student document. The link between the two documents is the student ID. The map function for the student collection looks like this. When we map the student collection, we expect to get the first and last names. We are concatenating or joining these together in a single value under the key name. Since the student collection doesn't contain information about the number of courses where a student is enrolled, this value is set to 0. This image may help to visualize what is actually happening. When the students collection is mapped, MongoDB iterates through the entire collection of student documents. This image may help to visualize what is actually happening. When the students collection is mapped, MongoDB iterates through the entire collection of student documents. For each student document encountered, it creates a new document, which it emits. So for Scott, it emits a document using the ID as the name and an array for the value. Since each student document emits only one thing, each array contains only one value. Looking closer at the document with an ID of Jeff, we can see that the map function first takes the ID value and then creates a document with two keys, name and number courses. The result that is sent to the reduce function is this document. There is one emitted document per key. In this case, we used a key that corresponds to an ID, which means that there is one emitted document per input document. The map function for the course collection looks like this. The course documents contain enrollment information grouped by course. What we're trying to do is instead group that information by student ID. In this case, we're mapping the contents of an array, so we use a for each loop on the student's array. It might be obvious that we will be emitting more items from this map function than the other, since a course may have many students. Since the course doesn't have the student name, we set that to an empty string. However, it's important to make sure that the structure of the document emitted from both map functions is the same, so they can be reduced later. Here we can see that the map function only encounters 3 documents, but emits 10 times. That's because there are a total of 10 student ID values in the students' arrays among the 3 course documents. We also notice that the emits are grouped. For example, we see that Scott's ID appears in the students' array for each course. This means that at some point in the for each loop for each course document, MongoDB will emit a document for Scott. When the first one is emitted, the initial interim document is created with the ID value. When subsequent documents are emitted with the same ID, they are added to the array. When developing and debugging map functions, it can be useful to confirm that the function operates on the document in the expected way. To do this, we can create a course variable and put one document into it. We must also create an emit function. All we need to do is print out the key and value. It is then possible to apply the map course report names function on the course and see that we get two values emitted. One is for Scott and one is for John. It is then possible to apply the map course report names function, which shows us that the first and last names were mapped as expected to John Shore. We can do the same by calling the map course report number function on the course variable and see that we get two values emitted. One is for Scott and one is for John.Shore. When we look at the course document, we see that that is as expected. When we compare that to the diagram of what we were expecting, we see that the student record does produce the expected output. Similarly, when we look at the course document, we see that we do get one John Shore document as well as one Scott document emitted for that course. In this video, we've been through the analysis of input documents to identify desired data. We then chose a common key value for our mapping from different collections. We used this information to create two map functions that emit just the data of interest in a shared format. In the next video, we'll create a reduce function to complete the processing of the course report. In this video, we will create a reduce function. This requires understanding the various document fragments that were emitted from our map functions and crafting a function that captures and assembles those fragments into a final representation, which we can store in a new collection. We remember that for our course report, we need to gather data from two collections, course and student. From the course collection, we get the sum of courses for a given student. From the student collection, we get the student's first and last name. Recall that the map output for courses is an array associated with a key value. The key value is the student ID. The array contains one document for each course with a value of 1. The array contains one document for each course with a value of 1. In the case of Lee 2331, only one course had him on the roster, so the array associated with his ID only contains one document. Scott, on the other hand, was registered for 3 courses, and the array associated with his name contains 3 documents. The purpose of the reduce function is to convert the array of values associated with a key and derive the desired representation. In our case, we want a sum of all courses. So for John.Shore, we want to end up with a document with a value of 2 for the key number courses. Recall that the output from the student map contained an array associated with a student ID value. The single value in this array is a document that contains the student's full name. In this reduce step, we want to update the output from the previous step, which calculated the sum of all courses in which the student is enrolled, so that it includes the student full name. So for Scott, we would end up with a document associated with his ID that contained his full name, Scott Mills, and a value of 3 for number courses. For our purposes, we can combine these reduce functions into a single function. Let's take a closer look at this reduce function. To begin with, we create a model of what we want the output object to look like. Notice that the map output for the course and student map functions includes a key and an array. The reduce function expects that key value and array value. We then loop through this array and increment the number courses value by the current value of number courses, or if the name value passed in is not an empty string, then we update the result with the name value that was passed in. Notice that in each case, we are updating the result object that we created at the top of the function. Finally, we return the updated result object. You may also notice that the key value is not directly used by the function. We can confirm the reduce function does what we expect by creating some local variables that mirror the output we expect from the map functions for both course and student. This is what the course map output would look like, and this is what the student map output would look like. When we call the reduce function with the student map output object, we get the expected result populated with the full name and a value of 0 for number courses. When we call the reduce function with the course map output object, we get the expected result populated with a value of 2 for number courses and an empty name. We're now ready to run the actual MapReduce against our collections. Since we have two map operations, one against the student collection and the other against course collection, we need to run two commands. You can also see that the test output above doesn't ever combine the result of number courses and name in a single document. We'll see how to do that in just a minute. First, we run MapReduce against the courses collection using this command. The MapReduce function expects the map and reduce functions as prototypes. It also accepts a JSON document describing such things as where to store the results. In this case, we are writing the result to a collection called course report and replacing anything that might have been in that collection. Recall that there are 3 courses with a total of 10 students enrolled. We see an input of 3. Likewise, if you've opened a new session since creating the reduce function, you'll need to input that again as well. First, we run MapReduce against the courses collection. The MapReduce function expects the map and reduce functions as prototypes. It also accepts a JSON document describing such things as where to store the results. In this case, we are writing the result to a collection called course report and replacing anything that might have been in that collection. Recall that there are 3 courses with a total of 10 students enrolled. It's important to also make sure you're still using the course tracker database. First, we run MapReduce against the courses collection. The MapReduce function expects the map and reduce functions as prototypes. It also accepts a JSON document describing such things as where to store the results. In this case, we are writing the result to a collection called course report and replacing anything that might have been in that collection. Recall that there are 3 courses with a total of 10 students enrolled. We see that there was an input of 3. We see that there were 10 emits, and ultimately there were 5 outputs. It's possible to interact with the collection that resulted from this MapReduce just like any other collection. When we call find, we see that there are 5 documents, each one having the correct value for number courses, but an empty name. Now we can run MapReduce on the students collection and pass in the map function to get student names. Notice that we provide the same reduce function. This time, rather than indicate that our output should replace previous data, we want to reduce. This tells MongoDB to merge the result with existing data when a key already exists. We know that there are 5 student documents and we expect a single emit for each, so these results make sense. When we issue a find against the course report collection, we see that the resulting documents now include both a full name and an accurate value for number courses. In this video, we examined the document fragments that resulted from the map functions. We then created a reduce function that would capture and assemble those fragments into a meaningful aggregate document, and we store these results in a collection for later retrieval. In the next video, we'll cover some advanced MapReduce techniques. In this video, we look at some advanced MapReduce functionality. We start by looking at the query functionality to target specific data to map and reduce. We then look at imposing limits for large data sets, which might be useful if a sample of MapReduce data is sufficient. Lastly, we introduce the idea of a finalize function for post-processing. In this video, we will be working with the same data we imported in the first video of the section. If you're starting with an empty server, you'll need to re-import the data from video 4.1. We'll also be using the same map and reduce functions we used to get number courses. You'll recall that the map number courses function looped over all student records and emitted 1 for each occurrence. The reduce number courses function summed those values, grouping by the student ID value. At this point, we can run a basic MapReduce using these two functions. Here we can see the enrollment for all students across all courses. Imagine that a professor wanted to know enrollment for just his course. The call to MapReduce can be modified by adding a query key with a document as a parameter, indicating the ID value of the desired course. For a review of querying in MongoDB, see video 2.4. When we run this MapReduce, the result is a list of students for just that course. In this case, we see 2 students enrolled. If we change the query to highlight a different course, we get the enrollment for that course. The query can be on any field in the document. For example, if we wanted to include every course that had received at least 1 rating of 5, we could run this query. Notice that some students are enrolled for 2 classes that achieved a rating of 5. Occasionally, it can be helpful to get some quick data out of a large data set. In these cases, it is possible to limit the number of documents using a MapReduce call like this. From the results, it can be seen that only 2 of the 3 courses were included. Sort can be a useful tool when using limit. In this example, we sort by the description, which gives us reports on a different 2 courses. At times, a final step is required to transform the reduce output into a final form. MongoDB accommodates this by allowing the definition of a finalized step or function. Data flows from map to reduce, and then to a finalize function to produce the final output. To see how finalize works, we'll change our map and reduce functions to focus on course ratings. These are values between 1 and 5, with a 5 being a perfect rating. The map course ratings function loops over all ratings and emits the rating and an incrementer value. These are associated with the course ID value. The reduce course ratings function sums both of these values, in one case producing a sum of all ratings, and in the other case producing a value representing the total number of ratings. Naturally, the sum of all ratings divided by the number of ratings gives the average rating. The finalize function does exactly that. Remember that the finalize function receives the output from reduce. It then divides the sum of ratings by the number of ratings and stores that value in a new document property, avg_rating. If we just run MapReduce without the finalize, we can see that the total emitted is 23, since there are a total of 23 ratings among the courses. We also see that the output is 3 documents, which matches up to the 3 courses. The output shows us the sum ratings and num ratings values. When we add in the finalize function as shown here, we expect to see a 3rd value introduced representing the average. And we see that the average was added. By adding a sort to the results on the average field, we can see the courses from highest overall rating to lowest overall rating. A similar sort could list them by total number of ratings or by any other value included in the output. In this video, we learned how to target MapReduce operations using query parameters. We also explored the use of limit and sort for large data sets. Finally, we learned how to use the finalize function to perform post-processing on reduce output. In the next video, we'll learn when it's appropriate to use MapReduce. In this video, we'll look at when MapReduce is a good fit. Common scenarios that call for MapReduce include when data is sharded and when data spans multiple collections. It's not a good fit for real-time queries. In the examples used in this training, the data about instructors, courses, and students exists in 3 collections. This made it a good candidate for MapReduce functionality. When you have data that spans multiple collections, MapReduce provides the flexibility to aggregate or reduce the data into a single collection. If additional details are needed, then additional MapReduce steps can be added to the process. A few of the MapReduce examples changed the format of the data and even performed calculations. Anytime these types of modifications or rearrangements of data are required, MapReduce may be a good fit. However, it's important to recognize that MapReduce isn't intended to replace join-type functionality in relational databases. In the case of sharded collections, MapReduce may be required to process data that spans multiple shards, especially where queries potentially span shard boundaries, which are always adjusting to balance the shard. MapReduce is generally not a good fit when real-time data is needed. MapReduce takes time to run, which can make for a bad user experience. However, the results of the MapReduce are stored in a collection, which can be queried easily in real time and updated when the MapReduce completes. Additional resources are available on mongodb.org. In this video, we review the scenarios when using MapReduce is a good fit and when it's not, such as real-time queries. In this section, we started with an overview of MapReduce, with a focus on understanding the data. We then created a map function and then a reduce function to produce a number of reports. Next, we looked at some advanced MapReduce functionality and the times when it makes the most sense to use MapReduce. In the next section, we'll learn about the aggregation framework. In this section, we explore the aggregation framework. We start with a review of the aggregation framework, followed by single-purpose aggregation and building up to aggregation pipelines. We then go through an aggregation example and a review of expression operators to perform sophisticated data manipulations. This first video provides a broad look at the aggregation framework. The concepts we cover include how aggregation transforms and summarizes data. Aggregation can be run in real time for some use cases and cached for others. We look closer at the aggregation modalities. Single-purpose aggregations are the first type. These are the most simple and are used frequently enough that they have individual implementations in MongoDB. They include count, distinct, and group. For more complex aggregations, MongoDB accommodates pipelines. These are run against a single collection and may include any number of stages. MapReduce, which was covered in Section 4, is another type of aggregation which can span multiple collections, accommodates sharded data, and provides the most flexibility. It's important to know which type of aggregation best fits a given use case. This table provides guidance when making that decision. In terms of complexity, single-purpose aggregation is the most simple. MapReduce is the most complex, with aggregation pipelines somewhere in between. In terms of speed, the single-purpose aggregation functions are specially optimized and run very fast. The speed of both pipeline and MapReduce depend on the number of documents involved and whether they span collections or shards. This could be very fast for small collections and slow for large data sets that span collections or shards. The utility of single-purpose aggregations is limited, while the pipeline is more broad and MapReduce is all-inclusive. Single-purpose aggregation can accommodate real-time queries. For small data sets with appropriate indexes, aggregation pipelines can be used in real time. For larger data sets, pipeline may be too slow. MapReduce always requires pre-processing. When selecting which type of aggregation to use, it's wise to follow these guidelines. Whenever a single-purpose aggregation accommodates application needs, use it. If more complicated transformations are needed, try aggregation pipeline first. If direct programmatic manipulation is required or data spans collections or shards, use MapReduce. In this video, we learned that aggregation is a tool used to transform and summarize data. Some forms of aggregation can be used in real time or cached, while others require pre-processing. Modalities available include single-purpose, pipeline, and MapReduce. In the next video, we cover single-purpose aggregation. In this video, we learn about single-purpose aggregation. Single-purpose aggregation includes functions for count, distinct, and group. The data for this section must be imported as in other videos. To do this, copy the bulk data import.js file to the server and import it using the Mongo command, as shown here. The downloaded project files include a Python script and other resources that make it possible for you to produce additional sample data if you want to. After importing the data, log into the Mongo shell and confirm that the collection is in place. A find can then be performed to see the structure of each document in the statistics collection. The single-purpose aggregation function, count, can also be used to get a count of records in the collection. You can see here there are 2,500 documents. The count function accommodates a query document. For example, the number of documents that have an action of download can be found with this command. There are 814 documents with an action value equal to download. Similarly, it's possible to get a count of all documents that reference a specific owner using this query. In this case, there are 15. It's even possible to get a count for the number of times a specific owner performed the download action using this query. The distinct single-purpose aggregation expects a field name as an argument. It then traverses the entire collection of documents to identify every distinct value of that field. Given the statistical documents shown, a call to distinct on the action field would produce an array containing 3 values: view, download, and update. In the Mongo shell, we can run that query and see that the output is indeed an array containing 3 values. This means that across all 2,500 documents, the only 3 values associated with the action field are view, update, and download. A distinct set of owner ID references can also be obtained using this query, and a distinct set of IP addresses using this query. The second argument to distinct is a query document. This can further limit the distinct function to operate on a subset of data. For example, the distinct set of IP addresses from which a specific owner made requests can be obtained with this query. In other words, requests originating from this owner were made only from this subset of IP addresses. Group is similar to distinct but adds summary details. As is shown here, calls to the group single-purpose aggregation function are somewhat more complex. The group function accepts a document which defines the details of the group aggregation to perform. The key element in this document is the key on which to group. A reduce function and initial variable state can also be provided as shown. Based on the data shown here, this call to group will get a count of every document occurrence and group that count under each of the 3 distinct values of action. You can verify this by summing the count from each of the 3 headings to get 2,500, which is the total number of documents. When this example is run on the Mongo shell, the expected result is shown. Suppose that details about each owner are desired. This query will count all records, but instead of grouping them by action, counts will be grouped by owner. As would be expected, each owner has fewer actions, in other words a lower count, than when the same data is grouped by actions, of which there are only 3. Taking this one step further, the cond element can be added to the document specifying a query condition. In this case, the count will be limited to documents with an action of view. Results will still be grouped by owner. As can be seen here, the numbers are still lower, which is expected because we're only grouping the documents with an action equal to view. In this video we learned about single-purpose aggregation. These include count, distinct, and group. In the next video we cover aggregation pipelines. In this video we discover the building blocks of aggregation pipelines. MongoDB offers a rich collection of pipeline operators to be used in sequenced stages. These operators include geoneer, project, and unwind, among others. Each pipeline operation works on the output from the previous operation. Some operators can only occur either first or last in the sequence. An unlimited number of operations or stages can be performed in a pipeline. First, we'll log into the Mongo shell and use our database and make sure that our collection is ready. Let's run a quick query to make sure we know exactly what our documents look like. The geoneer operator requires a special type of index to be built. Notice that each statistics document contains a field LOC for location, which contains values for latitude and longitude. An index can be created against these values using the 2D sphere index type. With a proper index in place, it's now possible to perform a geoneer aggregation. In this case, a point, comprised of a set of coordinates, is used to find documents near that point. Additional information, such as the distance between the 2 points and the point location, are also included in the output. Notice that these values are merged into each document when it is returned. An index can be created against these values using the 2D index type. With a proper index in place, it's now possible to perform a geoneer aggregation. In this case, a point, comprised of a set of coordinates, is used to find documents near that point. Additional information, such as the distance between the 2 points and the point location, are also included in the output. Notice that these values are merged into each document when it is returned. The group stage is similar, though semantically different from the single-purpose group function. In this case, the group occurs on the action field, and multiple group operators are used to summarize the data in those groups, such as min, average, and count of document occurrences. Limit works in the same way it does when appended to a standard query, except that it can now be used in aggregations to limit the number of documents that will be passed to the next stage in the aggregation. This example limited the result to 2 documents. Match allows for ad hoc queries. For example, this match will pass all documents with the specified object ID on to the next stage. Note that any query document will work, which includes advanced query techniques such as regular expressions. Project is a clever operator that makes it possible to restructure existing documents. First, notice that every field in the current document is accessible by prepending a $sign and wrapping it in double quotes. So in this aggregation call, the quote $_ID quote references the _ID value of the current document being processed, likewise for action and so on. This call to project effectively takes each input document from the previous stage, or all of them if this is the first stage, and outputs a document with the structure defined in the query. Here, _ID carries over, action is renamed to user action, and request time milliseconds becomes duration ms, as shown here. The result can be seen when this query is executed in the Mongo shell. Sort rearranges the output from the given stage to be ordered by the field identified. Output can be sorted in ascending order, a +1, or descending order, using a -1. Project is a clever operator that makes it possible to restructure existing documents. The unwind operator is useful for array fields. This operator explodes a single document into many documents, creating one new document for each element in the array. In this example, the array cookies contains 2 values, so the output includes 2 documents, one for each value in the array. This can be useful when combined with group and other commands operating against the previous array field, as we'll see later. When the unwind aggregation is run from the Mongo shell, each cookie value now represents a single value. All of the aggregation operators up to this point have been represented as a single document inside an array that is passed to the aggregate function. Multiple stages can be added by adding operator documents to this array, as shown here. The first stage projects each document as shown previously with an _ID, user action, and duration ms value. The next stage uses those values to group by action and find the minimum and average duration ms and the count of records under that grouping. Notice that the group doesn't reference request time milliseconds, but duration milliseconds. That's because the documents passed to it are defined by the previous stage, which is a project. The unwind operator is useful for array fields. This operator explodes a single document into many documents, creating one new document for each element in the array. In this example, the array cookies contains 2 values, so the output includes 2 documents, one for each value in the array. This can be useful when combined with group and other commands operating against the previous array field, as will be seen later. In this video, pipeline operators were reviewed, including geoneer, group, limit, and so on. It was observed that each stage in the pipeline operates on the data from the previous stage, and that unlimited stages can be performed by adding operator documents to the array passed to the aggregate function. In the next video, we will look at a more detailed aggregation example. In this video, we take a close look at an aggregation example. Just as with MapReduce, crafting an effective aggregation pipeline requires understanding the input data and desired output structure. The unwanted data should be filtered out and the pipeline crafted to achieve these goals. In this example, there will be 4 stages in the pipeline. The initial step will be to use match and group to derive a specific set of documents with some summary data. That data will then be projected onto a different format that breaks out and renames some key values. The final stage performs another projection which distills the key value and performs a calculation of some of the summary data. It is often best to build pipelines in stages, just as they will run. Building in stages also makes it easier to see the exact structure of the data coming into the next stage. In the first stage, a standard match is used. This reduces the result set down to only those documents with an action of view. The next step will group and summarize these documents. Since the timestamps are precise down to the millisecond, this group stage extracts just the month, day, and year as the grouping mechanism. In other words, it will group by day, regardless of when an individual document was generated. Next, it tallies up the number of documents, as well as the average, maximum, and minimum times of requests based on request time milliseconds. You can see here that the month, day, and year are broken out, and we now have the total number of requests made for that day, as well as the average time, max time, and min time for that day, for requests that occurred that day. The first project stage has 2 purposes. One purpose is to convert the year, month, and day into string values, whereas they were numbers after the group call above. This transformation will make it possible to concatenate the 3 values together in the next stage to form a single ID value. Casting directly to string is not possible in MongoDB, so instead a character of the substring function is used, which coerces the value into a string. Obviously, the entire string is used. The other transformation simply renames existing values for clarity. Now it's easy to see that month, day, and year are string values. In the 4th stage, which is also the second project stage, the year, month, and day values are concatenated into a single value. Additionally, it uses the subtract function to calculate the difference between maximum and minimum values, producing the gap between these 2 values. Other values are essentially passed through. So here we see that there's now a single ID value made up of a string representing the date. And we also now have a gap value, which is the difference between the maximum and minimum values. As a final stage, sort is used to order the data. In this case, the output data will be sorted by the average value, starting with the lowest average and ascending to the highest. At this point, the result is a collection of documents with an ID based on the month, day, and year that summarizes details about how long requests took to process. This includes the minimum, maximum, average, and the gap between the longest and shortest processing times. These values are all sorted in ascending order based on the average field. For this next example, geoneer is used in the first stage to identify all documents near a geographical point. The location of the point and the distance between the 2 points is also included. The second stage unwinds the cookies array. This effectively splits a document into multiple copies, one for each element in an array or list value. This is necessary as a precursor to grouping based on values that occur in the array. The output from the first two stages are all the documents near the given point exploded out into one document per occurrence in the cookies array. In the third stage, these documents are then grouped based on cookies, and a tally of occurrences is made. In other words, this tells how many times each cookie was found in an array. Exercise caution when using the unwind function, since subsequent stages could produce misleading results. For example, after unwinding the cookies array, there is essentially a duplicate of all document data for each value of the array. If the group stage attempted to find an average of the request time in milliseconds, the calculation would be flawed due to the extra data produced during the unwind phase. Here we can see the output after adding the group stage to our aggregation pipeline. In the final stage, the out function is used to write the result to a new collection named cookies near. For aggregations against larger sets of data which make real-time processing too slow, this caches the results of the aggregation in a way that can be indexed, queried, and further sliced. It can even be used as input to other aggregations. You can see that after running this query, there is no direct output. If we call show collections, however, we see that cookies near is now a collection. A simple find brings back the documents that resulted from the pipeline. In these examples, the input data and desired output determine the stages used in the pipeline. Available pipeline functions accommodate filtering and transforming data until the desired output is achieved. In the next video, we'll take a closer look at expression operators. In this video, we look at expression operators. Expression operators make it possible to perform sophisticated data manipulation on data in the aggregation pipeline. This may include analysis of data, arithmetic, string, and other manipulations. Comparison operators make it possible to perform comparisons between document values and fixed values. In this example, true is returned for any document with a request time in milliseconds less than 500, which is sub-half second response time. Here you can see in the first record, the request time is less than 500, and so sub-half second is true. In the next document down, however, 925 is not less than 500, so the sub-half second is false. Boolean operators make it possible to analyze various results. For example, in this query, the comparison operators greater than or equal to, greater than or equal, and less than or equal are passed to AND. The result is a value of true for any request between 1/4 and 1/2 a second, or 250 milliseconds and 500 milliseconds, inclusive. In the case of the first request, the request time is greater than 250 and less than 500, so it returns true. In the third item down, the request was completed very quickly in 37 milliseconds, but the between 1/4 half second value is false because that value doesn't fall within 250 to 500. It is also possible to perform advanced calculations on sets of data. In the statistics document is a cookies array or list. In this aggregation, isAdmin has a value of true for any document whose value for cookie exactly matches the array session admin. So in the first line, isAdmin is true because the cookies array is an exact match. The second line, however, is not an exact match, so isAdmin is false. It's also possible to find any document that contains a subset of values. For example, this query produces a value of true for the field has session, any document whose cookies array contains the subset session. So here we can see the first two are true, not because the arrays are the same, but because each array contains session. So in other words, it contains the subset identified. Arithmetic operations are often useful in aggregations. This aggregation shows an example where a value can be adjusted using multiplication to reduce the value by 20%. So as you can see, the first line here shows the request time is 379. So 80% of that or in other words, 0.8 times 379, gives 303.2. String manipulations are useful when summarizing text values. In this query, details about the action, request method, and request URI can be combined into a single comma-separated field. To lower is used to change the case of the fields that are stored in uppercase. Here we can see the values have been concatenated with commas separating them into a single string field, request summary. Array operators make it easy to get quick details about array fields. In this aggregation, the size of the array, meaning the number of elements it contains, is obtained using the size operator. Here we can see in the first record that the array contains two values, session and admin, so num cookies is 2. The next line down shows that it has 3 values, session, guest, and last page, and the num cookies is 3. Dates are frequently sliced and diced in different ways. The date operators make it possible to extract specific date parameters from a binary date field. These include elements like year, month, day of the month, hour, minute, second, and so on. These produce number values. Here we can see that each record comes back with split out values for year, month, day, hours, minute, and second. Accumulators work with the group operator to derive summary data, such as average, maximum, and minimum values. Here you can see that for download, we have an average, a maximum, a minimum, and a sum of the request time across all values. Expression operators make it possible to perform sophisticated data manipulation on data in the pipeline. These include analysis, arithmetic, and string manipulations. This section began with an overview of the aggregation framework. Single-purpose aggregations, including count, distinct, and group, were demonstrated. Aggregation pipeline was introduced as a mechanism to perform incremental transformations on data in stages. 2 advanced examples demonstrated the power of aggregation pipeline. A review of expression operators provided insight into what is possible with the aggregation pipeline. The next section will cover SSL security and programmatic access to MongoDB. This section covers the use of SSL to secure data to and from MongoDB and between nodes. It also covers access to MongoDB using programming languages. This starts with a process to build MongoDB from source in order to support SSL. The SSL-ready build is then verified and packaged for distribution to deployment servers. Authentication and authorization are explored, and programming examples using PHP and Python are shown. This video focuses on building MongoDB from source using Python scons. Prerequisites are installed prior to obtaining the MongoDB source. Scons is then used to build MongoDB. The build process requires a lot of disk space and memory. As a rule of thumb, plan on having at least 40 gigabytes of free disk space and 2 gigabytes of RAM. The build process also takes a while to complete, so plan enough time to let the build complete. The public MongoDB downloads do not support SSL. There are 2 ways to get an SSL-ready build of MongoDB. The first is to purchase an enterprise support license through MongoDB. The second is to build from source. In order to build from source on Ubuntu Linux, we need to install git, scons, libssldev, and build essential. We can install all of those with this command. Next, it's necessary to obtain the latest source code, which can be downloaded from the MongoDB website. In this case, wget is used to download the source. Next, the source is unpackaged using the tar command, and we change into that directory, after which the build process happens within the source directory. To give some context, I'm going to run the date command and copy the time into a text file. We'll compare this with the end time to complete when the build is done. In the most basic scenario, it should be sufficient to run scons --ssl all. By opening a duplicate session and looking at the top report on the server that's currently building scons, it can be seen that the build process takes advantage of only one processor. This means that adding additional processors for the build process won't speed the time to build. Now that the compilation is done, we have a current time given by the date function. The start time was 15:53:48 and the end time 17:29:56. which means that the total build process took 1 hour and 36 minutes to complete. A listing on this directory shows the binaries that resulted from the build process. We can use the df command to show that 75% of the disk is consumed. And the disk usage command shows that 27 gigabytes is consumed by files related to the MongoDB source or build process. Depending on your system, you may need to accommodate this size. In this video, the prerequisites of scons, libssldev, and build essentials were installed. The latest MongoDB source was obtained, and scons was used to build MongoDB from source with SSL support. The next video will show how to verify and package the binaries for distribution to production servers. This video shows how to verify and package the newly built MongoDB binaries for distribution. To verify the binaries, it's easiest to manually run them. The files that need to be included in the distribution to run on another system are identified. Finally, the process to package the files and transfer them to another system is demonstrated. SSL encryption requires a secure certificate. SSL certificates can be purchased or created. One benefit of purchasing a certificate is that most servers already include certificate authority certificates for many trusted vendors. In this video, an SSL certificate will be created instead of purchased. On the server, change into the etc SSL directory. OpenSSL is used to create two keys, one for the server and one for the client. In this command, to create a new key, the RSA length is 4096 using X509, and it expires in 365 days. It is possible to specify any number of days for the new certificate to be valid. Certificates will have to be replaced before they expire to avoid connection problems to MongoDB. One benefit to shorter times is that potentially compromised certificates are replaced sooner. After running this command, you'll be prompted to answer several questions. We'll accept the default values for all of these except for the common name, which we set to localhost. After running this command, there are two files, the cert file and the key file. The cat command is used to combine these into a single PEM file. This process is repeated for the client certificate. And again, the two resulting files are combined into a PEM file. Note that it's very important that you guard these certificates wisely. Anyone who gains access to these can connect to the MongoDB server that uses them. This command restricts access to these files to the user only for read and write purposes. A quick listing on this directory shows our new certificates and PEM files, and that our permissions are what we expect. The next step is to follow the manual installation procedure from section 1. We first transition into the build directory. Next, 3 directories are created inside of a Mongo directory. These directories are for data, logs, and the MongoDB binaries. A listing of this directory shows that all of the binaries of interest start with MongoDB, with one exception being the bsondump file. This makes it easy to copy them into the Mongo bin folder using this command. The bsondump file needs to be manually copied, and the Mongo A style, which was accidentally copied with the rest of the binaries, isn't required, so we remove that. A configuration file is required to start MongoD. In addition to the details mentioned in section 1, Manual Installation Configuration, there is a new section, Net, in which the port and SSL details are provided. There are various SSL modes. These range from allowing to requiring SSL for connections. In this configuration file, SSL is required, which means that non-SSL connections will be refused. Notice that MongoD.pem and MongoClient.pem are both referenced. The MongoD process can now be started with a reference to the configuration file that was just created. To accommodate testing of the MongoD process, we'll open a duplicate session, and we'll start by running the command psaux and grep for Mongo to show that the MongoD process is running. A tail on the log file also shows that MongoD is running and ready to accept connections. Finally, it is possible to connect to the Mongo shell. Notice that the command to connect is somewhat more complex since it now includes the port and references to both the client and server PEM files. We're successfully connected to MongoDB over SSL. We can now exit out of this second shell and kill the MongoDB process. In order to package up the files, we return to the home directory, and note that the only files that need to be packaged up are those in the Mongo bin directory. This makes it possible to follow the same manual installation process outlined in Section 1 to install the SSL ready build later on. This tar command will create a new file and add all the files in the Mongo bin directory to it and compress them using gzip compression. While these zip up, it's important to note that the build depends on the system architecture. If the build was performed on a 64-bit machine, then it is effectively a 64-bit distribution and won't run on 32-bit systems. A 32-bit build may run on both platforms, but there are MongoDB features that are not supported in the 32-bit build. The MongoDB binary files are very large, which means the process of zipping them up can take quite a while. A listing on the directory shows us that we now have a packaged MongoDB binary SSL distribution ready to deploy to our own servers. In this video, the SSL ready build was verified and the binary files were packaged into a compressed tar file. The manual installation process from Section 1 accommodates installation and management of MongoDB builds. SSL certificates are required and can be either purchased or created depending on your needs. The next video will cover authentication and authorization. This video covers authentication and authorization in MongoDB. Authentication is specific to a database, which means that each database can have distinct users, even if those users have the same username. The process to set up authentication and then use that authentication is covered. It's important to understand the difference between authentication and authorization. Authentication confirms a user's identity by way of credentials. Authorization defines what the user is allowed to access. One example would be that a person may have keys to get into a building, authentication, and still not have permission to enter every room in that building, authorization. Another example, a person may have a driver's license, which is identity and authentication, but not be authorized to operate commercial vehicles, authorization. The first step to enable authentication is a change to the Mongo CFG configuration file. A section, security, is added to the file and authorization is enabled, as shown here. The MongoDB process can then be started and the Mongo config file indicated, as shown here. Leave the MongoDB process running here and open a duplicate session. Some data will be needed later in this video. Copy the bulk data import.js details onto the server so it's available for a future step. Connect to MongoDB using the Mongo shell. Recall that for SSL use, it's necessary to identify the certificates to use. It's also important to note that since the MongoDB process was started with authorization enabled and there's not yet a user created, this connection must be made from the local host. First, use the admin database, then call the dbCreateUser command to create a user. In the document passed to create user, the username and password and user roles are included. It is also possible to include a custom data field, which is ignored by MongoDB, but may be useful from an organizational perspective to store metadata about system users. In this case, the user is given a username of admin, a password of secret, and the roles user admin, DB owner, and restore. Exit the database and reconnect to show the effect that authentication has now that a user has been added. Notice that MongoDB allows connections to the Mongo shell, but prevents any access until authentication and authorization have been performed. Authentication is performed by way of db.auth and providing a username and password. The one indicates success. However, the showDB's command still fails. Notice the message says the user is not authorized to show DBs. The function showDBs requires the user to have read-write privileges. This role can be added to the admin user with this command. Notice that after adding this role, the admin user is now able to show DBs. As the admin user, use the statsdb database. The load command can now be used to import sample data from the bulk data import.js file. The response of true indicates that the data was successfully imported. Create two users to interact with the data in the statsdb database. The first user will accommodate read-write access and has a username of statsdb_rw with a password of secret and a role of read-write on the statsdb database. The next user will accommodate read-only access and has a username of statsdb_ro with a password of secret and a role of read. Exit the Mongo shell and reconnect. Notice that after using the statsdb database and trying to show collections, an error is displayed. The database requires a user to authenticate first, which can be done with db.auth as shown. A 1 indicates success. This user is now authenticated and can show collections. The user can also query for records. However, when authenticated as the statsdb RO user, it is still not possible to insert a record, as can be seen by the error message after this command. In order to insert data, first authenticate as the statsdb RW user with this command. It's then possible to insert the desired data and also query to find that it was inserted as expected. It's important to give careful thought to the roles assigned to specific users. For example, if the admin user will be used in a restore scenario, that user must have the restore role. Similarly, the user management role should be carefully administered. This video introduced authentication, which occurs at the database level. The process to set up authentication was illustrated, and how to authenticate at the Mongo shell was demonstrated. The next video will show how to use PHP to access MongoDB. This video covers the use of MongoDB through the programming language PHP. PHP-related libraries are installed, as well as those required by MongoDB. Examples are then used to illustrate connecting to, querying, and managing data in MongoDB. This example can be run from the same server or another server. For this video, the same server is used for convenience. On Ubuntu Linux, the apt-get system is used to install PHP 5 and PHP 5-Mongo using this command. Once the installation completes, the presence of PHP can be confirmed using this command to output the PHP version. In this case, the secure certificates are on this server. If another server is used, the PEM files would need to be copied over to that other machine. This first example script will fetch data from MongoDB and display it. In order to connect, a context object is created that identifies the secure certificate files. A connection is established by creating an instance of the Mongo client class. The connection URL includes the username and password for authentication and the domain, port, and database. An array indicating that SSL is required and providing the context are passed as arguments to the function. Once the connection is established, a handle to the database can be obtained from the Mongo client instance M. In similar manner, the statistics collection can be obtained from the DB handle. Finally, the statistics collection handle can be used to run a query against the database. var_dump is used to output the record that was returned. In order to run the script from the command line, we add the executable bit. From the command line, the script can be run by simply calling it. The output is formatted in typical var_dump structure. With some small changes to the initial script, it's possible to create a new document, sequence.php. In this script, it's possible to create and insert a new document into the collection. Notice that for specialized MongoDB field types, like date and object ID, special PHP classes are used. Since arrays in PHP are associative, this maps well onto the JSON data format used in MongoDB. Insert can then be called on the collection handle to add the new document. Finally, a slightly modified find_one call on the statistics collection limits the document retrieval to documents with a request IP of 0.0.0.0, which is the IP provided in the inserted document. Again, we add the executable bit and run the script from the command line as shown here. The script produces the expected output showing that the new document was added to MongoDB and then retrieved by the find_one call. In this video, the PHP and Mongo related libraries were installed, and 2 example PHP scripts were used to illustrate how to connect, query, and insert new data in MongoDB. The next video will cover the use of the Python programming language to access MongoDB. This video covers the use of MongoDB through the programming language Python. Python-related libraries are installed, as well as those required by MongoDB. Examples are then used to illustrate connecting to, querying, and managing data in MongoDB. This example can be run from the same server or another server. For this video, the same server that's running MongoDB is used for convenience. On Ubuntu Linux, the apt-get system is used to install Python setup tools and Python pip, which is then used to install PyMongo. The installation can be verified by opening a Python shell and typing import PyMongo. If no error is displayed, then PyMongo was successfully installed. Python has 2 major language versions, Python 2 and Python 3. The default version on Ubuntu is Python 2, which is what is installed using the commands already shown. A slight modification can be used to install setup tools in Python 3, which can then be used to install PyMongo for Python 3. The availability of PyMongo in Python 3 is obtained the same way as before, but from the Python 3 shell. In this case, the secure certificates are on this server. If another server is used, the PEM files would need to be copied over to that other machine. This first example script will fetch data from MongoDB and display it. The SSL library must be imported, as well as the Mongo client class from the PyMongo library. An instance of the Mongo client class is created by sending in a connection URL and details about how to connect using SSL. The connection URL includes the username and password for authentication and the domain, port, and database. Once the client connection is established, a handle to the database can be obtained from the Mongo client instance. In similar manner, the statistics collection can be obtained from the DB handle. Finally, the statistics collection handle can be used to run a query against the database. Print is used to output the record that was returned. We add the executable bit to this script and can run it from the command line as shown here. The output is formatted in typical Python dictionary structure, which looks very similar to JSON data. With some small changes to the initial script, it's possible to create and insert a new document into the collection. Notice that for specialized MongoDB field types, like date and object ID, additional Python libraries must be imported, like datetime and the PyMongo object ID. Dictionaries in Python are strikingly similar to JSON documents, which maps well onto the JSON data format used in MongoDB. Insert can be called on the collection handle to add the new document. Finally, a slightly modified find_one call on the statistics collection limits the document retrieval to documents with a request IP of 1.1.1.1, which is the IP provided in the inserted document. Again, we set the executable bit and can run this script from the command line as shown here. After running this script, we see the expected output showing that the new document was added to MongoDB and then retrieved by the find_one call. In this video, the Python-related libraries for MongoDB were installed. 2 scripts were then used to illustrate the use of Python to query, store, and otherwise manage data in MongoDB. In this section, the process to build MongoDB with SSL support was established. The resulting build was then verified and packaged for distribution. Authentication and authorization were demonstrated, and examples in 2 programming languages, PHP and Python, were used to illustrate programmatic access to MongoDB. The next section will cover replica sets for reliability and scale. In this section, we cover replica sets to achieve reliable and high-performance deployments. Replica sets are made up of various node types. After reviewing these node types, a replica set will be built and then failover verified. Write concern, which allows levels of data consistency, is then discussed, followed by read preference and how load can be distributed across nodes in a replica set. This video focuses on a discussion of node types. Before discussing the node types, it's important to understand that replica sets ensure multiple copies of data are available. Replica sets need to exist in odd numbers in order to ensure that a new primary can be elected. All writes go to a primary, while reads can be distributed. Nodes can be added to a replica set with a few purposes. Two main distinctions are regular and arbiter. Regular nodes function as secondary nodes and can take over the role of primary node in the event of a failure. In some cases, a regular node has restrictions introduced so it can fill a special purpose. One example is to create an active backup. One motivation for this is to provide a node that won't respond to queries or be promoted to primary, but which contains a full copy of the data that can be used to create backups. Another special purpose use might be a system that is intended only to respond to queries but not writes, so it can never become primary. When looking at the different node types, this table can help make decisions about system configuration. For example, a typical node will have high memory and disk requirements, plus high bandwidth to accommodate read and potentially write traffic. An arbiter, on the other hand, requires minimal memory and disk and very little bandwidth. An active backup configuration may not have high memory requirements since it won't actively be handling reads or writes. Bandwidth requirements should be sufficient to replicate data from active nodes, and sufficient disk space should be provided to hold all the data. Replica sets ensure multiple copies of data are available. They should exist in odd numbers so that elections for a new primary do not fail. All write traffic goes to the primary, but read traffic can be distributed among all active nodes. Some nodes may have a special purpose or even have the role of arbiter. In the next video, we will build a replica set. In this video, we build a replica set. This process includes installing additional instances of MongoDB and subsequently adding those as nodes in the replica set. Finally, all hosts are verified to show they are active. There is a utility on Linux called screen. The screen command makes it possible to run multiple shells from a single login. This is used throughout this tutorial to make it possible to start multiple MongoDB processes that will serve as nodes in the replica set. This tutorial also makes use of the manual installation process to more easily run multiple MongoDB processes from a single shell. Start by downloading the latest distribution and unpacking it in the current directory. Next, run a sequence of commands to create individual data directories for each node in the replica set, as well as a logs directory to hold all log files. The first instance of MongoDB is started with this command. The combination of options -D and -M tells screen to start this shell in detached mode. The $S specifies the label to give this screen so that it's easy to identify in the future. The next argument is the command that should be run in the shell that's created. In this case, MongoDB is being started with a number of arguments that would normally be included in a configuration file. In this case, it's more useful to see them in the command call, so they are left as arguments to the call to MongoDB. Notice that the name of the replica set is given as rs0. It is now possible to verify that the MongoDB process is running in a few different ways. First is with a psaux command, which shows that the MongoDB process is running. Another way is to tail the log, which shows that the MongoDB process is running and waiting for connections, but also looking for more information about the replica set. Finally, it's possible to run screen-ls, which shows it running as a detached screen shell. The next two nodes, rs2, rs3, and the arbiter, can be started quickly using similar commands. Notice that the primary difference between each command is the label given to the screen shell and the port assigned to the MongoDB instance. Naturally, the data directory and log file name represent the different processes. The screen list command now shows all 4 instances running. To set up the replica set, connect to the first MongoDB instance in the Mongo shell. It's possible to connect to any of the nodes just by changing the port argument, since they are running on distinct ports. Create a replica set configuration document as shown. This must reference the replica set name that was identified when the MongoDB process was started. In this case, it was rs0. The members of the replica set are also given. Right now, only a seed member is given as the current member. This rsconf document can now be used to initiate the replica set using this command. The configuration can be verified by calling rs.conf. Additional nodes can be added using the command rs.add and providing the connection URL, which we repeat for both 18 and 19. The arbiter is added using rs.addArb and providing a connection URL. The replica set status is shown using the rs.status. Notice that the replica set is set up and configured with 1 primary, 2 secondaries, and an arbiter. The primary is running on port 2717. It's also noticed that the Mongo shell now changes to show that this Mongo shell connection is to the primary. Replica sets are easily set up by adding nodes to a configured replica set. The commands rs.conf and rs.status provide real-time details about the configuration and health of the replica set. In the next video, we verify failover of our replica set. In this video, the failover of an existing replica which loses a member is verified. First, the health of all nodes is verified. One node is then removed to simulate a system failure. Lastly, we confirm that if the primary goes away, a new primary is elected and the replica set remains responsive. This video assumes that a system is in the same state that it was at the end of video 2 of this section. It can be confirmed that all expected instances of MongoDB are running using the screen list command. Use the Mongo shell to connect to the first running instance of MongoDB. The command to connect should indicate the port 27017. It is now possible to get the current status of the replica set using rs.status. Based on the status output, the first node running on port 27017 is the current primary. From the screen output, the ID for that instance is 1362. For these next commands, we'll create a duplicate of this session. That instance of MongoDB can be destroyed using the screen command with the -x and -s options and providing the ID for the instance that needs to be killed. This will simulate a server failure. A listing of existing screens shows that Mongo-rs1 is no longer running. Notice that back in our previous Mongo shell, when rs status is called, the command fails, since that server was killed. In order to get the current status of the replica set, it's necessary to connect to one of the other running instances. In this case, we'll choose 27018. Showing the status again, it is seen that the host previously assigned as primary now shows as down or unhealthy. The election occurred, making node 3, running on port 27019, the primary. Note that this took only a few seconds for the system to notice the MongoDB instance went away and to compensate for it. The fact that a new primary was elected already means that write traffic will continue to succeed, resulting in minimal downtime, if any. The first node can now be started again using the screen command from before. A listing of screens shows that it is now running. The status of the replica set can now be checked again to confirm that the node is available. It now shows that the MongoDB process was reintegrated and that it is functioning as a secondary. Notice that when the MongoDB process was restarted, no additional intervention was required to reintegrate it into the replica set. The remaining nodes observed that it was available, and the reintegration happened automatically. Depending on the volume of transactions that were missed, the node may show in a state recovering, while replication makes the node consistent with the rest of the replica set. In this video, the replica set was examined to confirm that all nodes were active and healthy. One of the nodes was then removed and failover was verified. When the host was started again, it was successfully reintegrated into the replica set. The next video will cover write concern, which affects responsiveness and consistency. In this video, write concern is explored. Write concern determines how MongoDB responds to writes. The choice of write concern levels depends on the desired level of consistency, redundancy, and responsiveness. A few examples of write concern are then demonstrated. The concept of synchronicity is required to properly understand write concern. A synchronous process occurs in sequence. The actions must take place in a predefined order, preventing later steps from starting until earlier steps complete. Asynchronous, on the other hand, means that steps may occur in parallel. Responsiveness has to do with the user's perception of how quickly the application responds to input. Highly synchronous applications can feel less responsive because all steps must complete before the user can give another command. Asynchronous applications can feel more responsive because the previous command doesn't have to complete before allowing the user to give another command. Write concern tells MongoDB whether steps must occur in sequence or if they can be done in parallel. Data consistency is the level of assurance given that data will be exactly the same on all nodes in a replica set. If data consistency requirements are low, then write concern could lean toward asynchronous. If data consistency requirements are high, then write concern should lean more toward synchronous behavior. Unacknowledged is effectively asynchronous. This write concern tells the Mongo client to send a write and immediately move on. The Mongo client doesn't even wait for the MongoDB process to respond that it received the request. The default write concern is acknowledged. In the case of acknowledged, the Mongo client will wait for the MongoDB process to respond that it received the request. However, that doesn't mean that the MongoDB process has done anything at all with it. The journaled write concern level instructs the MongoDB process to respond only after the write has been written to the journal on disk. The next level, replica acknowledged, has various degrees. In this case, the MongoDB process is instructed to respond only after the write has been written to the primary and replicated to one or more nodes in the replica set. Tags can be associated with nodes in replica sets that may span rack, network, and even data center boundaries to ensure the highest level of data consistency. In this example, the document is to be written to a majority of the nodes and should time out if this doesn't occur in 3 seconds. Other values for W that are acceptable include 0 for unacknowledged, 1 for acknowledged, or a higher number to ensure that the data is written to the specified number of nodes. It can also provide the name of a tag set to ensure that it is written to nodes in that tag set. In this insert call, with W set to 0, the Mongo client won't wait at all before returning. So notice that the write result is empty. In this video, synchronicity was explained and applied to write concern. The various levels of write concern make it possible to balance application responsiveness with data consistency needs. An insert query was shown that required data to be written to a majority of nodes before returning. The next video will cover read preference and load distribution. This video looks at read preference, which makes it possible for MongoDB to distribute query load between nodes in sophisticated ways. Proper use of read preference requires understanding consistency and speed needs in order to identify data priorities. A demonstration of read preference is then given. This section makes use of PHP and Python to show read preference functionality. Additional details about using those languages with MongoDB is available in Section 6, videos 4 and 5. Read preference makes it possible to suggest to MongoDB how it should route read requests among nodes in a replica set. Read preference modes include primary, primary preferred, secondary, secondary preferred, and nearest. If an application has high data consistency requirements, choosing a read preference of primary can reduce the risk of getting an inconsistent read, since all data is written first to the primary, but replication to secondary nodes may lag. Primary preferred allows an application to send a request to secondaries if the primary is not responsive enough. Secondary requires read requests to go to secondaries, which makes sense in scenarios where the primary needs to be 100% available for writes. Secondary preferred will still allow reads to go to the primary, but a secondary is the top of the list. Nearest nodes are determined based on latency. Depending on network, current load, and other factors, this list may change and has no direct relationship to geographic or physical proximity. Nearest functions the most like a smart load balancer in that it continually tracks ping time to other nodes so that requests can be routed to the lowest latency nodes. It is possible to tune transaction throughput for both reads and writes by choosing an appropriate read preference. While read preference and the distribution of reads across multiple nodes does increase throughput somewhat, the preferred mechanism for scaling to very large datasets for high volumes of transactions is sharding, which will be covered in the next section. In order to run these commands, it's first necessary to install PHP 5 and the PHP Mongo library, as well as Python setup tools and pip, to then install PyMongo. In PHP, the read preference can be set on the instance of a Mongo client, as shown here. After setting this once, all subsequent requests will be routed to the nearest node for processing, which may include the primary. The executable bit is set, and read preference can be executed. In Python, the read preference can be incorporated into the instantiation of the Mongo client object, as shown here. In this case, all read requests will now be routed to a secondary. We set the executable bit and run the Python script. This video covered read preference as it related to data consistency and distribution of read requests among nodes in a replica set. This makes it possible to set data priorities. It concluded with 2 examples in PHP and Python to use read preference. This section started with a discussion of the types of nodes in a replica set. It then went on to build a replica set and verify that failover and recover functioned as expected. Write concern and read preference make it possible to determine various aspects of application responsiveness and address data consistency needs. The next section covers some advanced topics for MongoDB, including sharding. This section looks at several advanced topics in MongoDB. The section begins with a review of sharding for large-scale applications. The focus then turns to the Mongo Monitoring Service, or MMS, which can be used to deploy, monitor, upgrade, and back up MongoDB installations. The section finishes with a review of caching techniques to make MongoDB even faster and more scalable. This video focuses on sharding and scaling in MongoDB. Sharding is reviewed at a structural level to understand how data is partitioned, such as shard keys, and the deployment implications of sharding, such as increased hardware footprint. The typical deployment that has been discussed in previous videos has MongoDB processes running on servers that are then assembled into a replica set. Client connections interact directly with MongoDB processes. This scenario is straightforward and provides some load balancing among nodes in the replica set. In a sharded scenario, several aspects of a deployment change. The first, and most notable, is that the client no longer communicates with the MongoDB instances directly. Instead, a new component called MongoS is introduced. The reason for this is that after data has been sharded, which is to say partitioned, the client doesn't know on which replica set a given piece of data is stored. The MongoS instance is designed to route queries to the appropriate MongoDB processes. The MongoS process will most often run alongside the application or on a very lightweight server, since all it does is route traffic. MongoS knows how to route queries thanks to the config servers. These store metadata about sharded data. It is recommended that at least 3 config servers be deployed for reliability. Each config server contains the same information. A complete replica set is now required for each shard. This provides for reliability and failover at a data level. The config servers will work to ensure an even distribution of data across shards. Note that if a large volume of queries are made for data that is on a single shard, the other shard is largely idle and doesn't increase throughput. For this reason, it's important to choose the right shard key. A shard key is a field of a document that will be used to partition the data. For example, if a collection held documents representing people and the last name field was chosen as the shard key, then MongoDB would use the last name field to distribute the data. Keep in mind that if a collection of people documents contains many last names that start with A and C, then sharding would not necessarily split in the middle of the alphabet. It would split in the middle of the data. It's very important to choose a shard key that is likely to result in a distribution of queries among shards. This section introduced sharding in MongoDB. Sharding is how MongoDB partitions data to distribute work. Data is segmented based on a shard key. The number of servers required to set up a sharded cluster is much higher than what is required for just a replica set. The next video will present a sharding example. This video presents a sharding demonstration. The replica sets are created and data imported. Next, the config servers are created and a MongoDB server is also started for client access to the shards. Finally, the shards are added and sharding is enabled for the database and collection based on a shard key using request IP. As in previous videos, the MongoDB binaries are downloaded and unpackaged in the current directory. A directory to contain log files is also created. This video makes use of the Linux screen utility, which was used in previous videos. The bulk data import.js file contains data that will be required for later steps. Now is a good time to import that data. In order to build the first replica set, the data directories must be created. In this case, the directories are placed in a directory S1, indicating the first shard. The screen commands will start the MongoDB instances. The screen list command shows that 3 new servers are running. It is now possible to connect to the first server using this command, and from the Mongo shell, the replica set is initiated. The second server and arbiter are added to the replica set. Now, rs.status shows the servers in either primary or startup state. Now that the replica set is up and running, we use statsdb and the load command to import the data. A quick count on the statistics collection confirms that the records were successfully imported. We now exit out of this first replica set. These same steps are repeated for the second replica set. First, the data directories are created, this time using a directory called S2. The screen commands start the servers. Notice that the port numbers are distinct from the first replica set. Now connect to the first server in this second set and create the rsconf document. Notice that the ID value is rs1, whereas the first replica set is rs0. rsinitiate is called with the rsconf file, and the second server and the arbiter are both added to the replica set. rs.status shows that the servers are either available or in startup mode. Exit from the Mongo shell and proceed to the next step, which is to create the config servers. Note that the config servers do require a data directory. The port numbers are distinct from other servers since we're using screen and running all servers on the same host. Finally, the MongoDB server is started. Notice that MongoDB is running on port 27200. This is the port that will be used for client connections since MongoDB is the gateway to a sharded system. Calling the list command on screen shows that there are 10 servers running and all required components are represented. It's now possible to connect to the MongoDB shell using the same command that would be used to connect to MongoDB. The only indication in the connection string is the port being specified. From the MongoDB shell, each of the replica sets needs to be added. First, the rs0 shard is added, followed by the rs1 shard. At this point, any regular Mongo shell command can be executed. To enable sharding, first use statsdb. Next, call sh.enableSharding and provide statsdb as the database to shard. Statsdb is now ready to shard. Before a collection can actually be sharded, an index needs to be created to accommodate the shard key. For this example, the shard key will be a combination of the request IP and the _ID values. What this means is that documents will be sharded based on request IP. If there are records that have the same request IP, these will be sharded based on _ID. Everything is ready to shard the collection, which is done with this call to sh.shardCollection. The first argument indicates the database and collection to shard. The second argument indicates the shard key. The shard status can be seen with this command. Notice that right now the distribution of records shows that all data exists on the RS0 shard. In order to see sharding at work, it's helpful to have a little more data than is currently in the statistics collection. In order to get some more data, some JavaScript functions can be created. The getOctet function is used to create components in an IP address. The methods array and the actions array make it possible to somewhat randomize the character of each record. Finally, this loop will add 25,000 new documents to the statistics collection. Showing the getShard distribution again indicates that the data has begun to be distributed between the shards. In this video, 2 replica sets were created. Config servers and a MongoDB server were also created. These were used to set up a sharded environment and shard the statistics collection based on request IP. The next video will walk through the setup of MMS. This video will focus on the setup and use of Mongo Monitoring Service, which is called MMS. The Mongo Monitoring Service originally had only a monitoring focus. Over time, the automation tools that emerged provided functionality that included backups. Today, it also accommodates deployments, upgrades, and tuning guidance. The first part of this process takes place on mms.mongodb.com. Legacy MMS accounts won't include this functionality. After registering for a new account, click the Begin Setup button. It is possible to use MMS to deploy to a local system, AWS, or other. Since this training is making use of DigitalOcean servers, the other remote option is selected. For this example, we choose replica set as the deployment type and provide a name for this deployment, such as pact MongoDB. Identify that 3 servers are desired. The data directory can be left with the default path /data. Choose Continue. Choose whether to enable backups. For now, I'll choose not to include backups. On any virtual server provider, create 3 new servers to which MongoDB will be deployed. Be sure to size these appropriately based on the role MongoDB will play. Since they will be acting as nodes, they should be sized similarly. In this case, I have also provisioned each server in a different availability zone, but in the same region to balance reliability and latency. These servers will need to be able to see each other on the network. MMS derives the name for each host using the Linux hostname command. This means that either the hostnames need to be fully qualified domain names and DNS set up to associate the correct IP address, or the etc hosts file needs to be modified to identify each host. In this case, the etc hosts file is updated to associate each host name with its IP address. The etc hosts file is updated, as shown here, to accommodate access to all hosts. It's now possible to ping these hosts by hostname. The same modification to the host files on the other 2 systems are required. The next step is to download the automation agent from MMS. Click on the Download Agent link and choose your operating system. In this case, we're using Ubuntu. Down below the server boxes appear instructions for downloading and installing the agent on the chosen platform. In this case, a curl command is used to download the automation agent. And dpkg is used to install the package. The next instruction is to edit the config file and replace the existing MMS group ID with the one provided, as well as the MMS API key. Save changes and exit. Next, the data directory must be created, and ownership on that data directory set to the MongoDB user and group. The agent can then be started, and back at mms.mongodb.com, click Verify Agent, at which point the agent turns green. This process is repeated for the second replica set node, and verify the agent for the second host, and repeat for the third and final node, and verify the agent on the final third node. At this point, the automation agent is running on all three machines, and they all show green. Click Continue, and under Review and Deploy, notice that only one node is given a monitoring agent. This means if that node falls out, there is no redundancy in monitoring. To add another monitoring agent, choose either of the other hosts and click Install Monitoring Agent. You'll notice the gray empty circle, which is an indication that it will be installed. Once you've made all the necessary changes, click Deploy. MMS then walks you through a series of messages about how the service works. From the Edit mode or View mode, we can see that the nodes are in the process of coming up, while MMS deploys and configures the software we requested to each node. MMS shows that the servers have been successfully deployed. From the View mode under Deployment, it's possible to see that we have one primary assigned to MMS Mongo 1 with two secondaries, MMS Mongo 2 and MMS Mongo 3. To simulate a server failure, the first node can be shut down. Notice that MMS quickly notices that the host went away. The remaining agent takes over the monitoring function, and a new primary is elected. In this case, MMS Mongo 2. If the server is then powered back on, it will be automatically reintegrated into the replica set. Here it can be seen that MMS Mongo 1 has not only been reincorporated, but assigned secondary in the replica set. In this video, the setup and basic use of MMS was demonstrated, which included deploying a 3-node replica set on an arbitrary cloud hosting provider, DigitalOcean in this case. In the next video, some more advanced features of MMS will be reviewed. This video walks through some key features of MMS. In particular, this covers how MMS can manage deployments and versions. Alerts related to system states are shown, including views into system activities. Database backup is reviewed, as well as general administration. From the main deployment page, all deployments can be seen. This view shows the healthy 3-node replica set that was created in the last video. Edit mode shows either a topology view, which is the default, or a server view, which shows all of the components installed on each system. From the server view, it is possible to manage the automation components that are running on each server, such as monitoring or backup. From the version manager page, the various releases of MongoDB are viewable. From this page, it is also possible to add custom builds. The activity page shows the most recent activities. For example, it shows that MMS Mongo 1 was restarted, which is how it interpreted this host shutting down and then coming back. If the host had been left down long enough, it would have triggered a host down event. The Alerts Settings subpage makes it possible to add alerts for specific events. By clicking Add Alert, we can see that alerts may relate to host, agent, backup, etc. For example, an alert can be created for a replica set to trigger when no primary is found. The second step makes it possible to limit the scope of the alert to a specific replica set or all replica sets associated with this account. The alert can be sent to users, groups, emails, and even SMS, among other options. The timing of when an event is triggered can be defined. Backups accommodate a free usage tier, which includes up to 1 GB of data. Backups work by copying oplog data. The oplog, or operations log, is how MongoDB captures changes made to the primary so that they can be replicated to other nodes in the replica set. The backup is treated like another node and captures data the same way secondary nodes do. Keep in mind that the data is sent to and backed up on MongoDB servers. Think carefully about the sensitivity of the data before choosing this as a backup option. From the administration menu, personal details, accounts, and groups can be accessed. API access credentials and security settings are also available. This section also includes billing details for use with this service. The MMS offering provides some compelling features in terms of automation and deployment. These must be balanced against data sensitivity needs, SSL and encryption requirements, and the size of a deployment. If a project's budget accommodates the use of MMS, it is a strong contender for managing deployments, monitoring, backups, and upgrades. This video reviewed some key features in MMS, such as deployment and version management. Alerts and activities were also reviewed, as was the backup and general administration functionality for MMS. The next video will look at additional caching options for ultra-high-scale websites with strict performance requirements. This video will focus on additional caching approaches that can complement MongoDB. Specifically, this will cover what caching is and where it can occur. Language-specific technologies like APC, as well as Memcache and Redis, can be combined with MongoDB for significant performance improvements. It's important to recognize that MongoDB will make use of all the free memory that is made available to it. Obviously, the best performance will be achieved when the entire working dataset fits in RAM. However, this doesn't account for post-processing after the data has been retrieved or network latency involved in getting the data from MongoDB to application servers. As a result, it can be advantageous to provide additional caching. Caching can occur at various levels. From a traditional 3-tier application perspective, caching can be introduced at the web tier, the application tier, or the data store tier. Each application will have a sensible place to position this caching, but each will be different. At the web tier, varnish may make sense. This would be a fit when a rendered page will be identical across many requests. When there is a combination of dynamic and static components, so that each rendered page is different, it may make more sense to cache at the application tier. Technologies like EHCache for Java or APC for PHP may make sense in this scenario. Occasionally, large datasets or slow-running queries at the database level may provide an opportunity for caching. In cases like this, an in-memory cache, such as Memcache or Redis, could be used to great advantage. The following example script expects to communicate with a sharded system identical to the end result from video 2. Some additional setup is required. For example, we use this command to install PHP 5, PHP 5 Mongo, and PHP APC. Next, the PHP ini file for command line interaction is modified to enable the command line use of APC caching. In this example PHP script, a connection to MongoS on port 27200 is made. This block retrieves a record for the given ID value directly from MongoDB using find1. A message is then printed out showing the ID of the object returned. The time to perform the operation is then calculated and printed out. The document is then added to the APC cache and the process is repeated, except that this time the document is retrieved from the APC cache. The time to perform the cache retrieval operation is calculated and printed out in milliseconds. As was mentioned, the end state from video 2 of this section is expected. This means that the screen list command shows a running sharded deployment on this single machine. Since the PHP script will be run from the same machine, there will be no network latency. The timings produced should reflect only the overhead required by MongoDB to perform the query and retrieval compared to the APC cache mechanism. On the first run, the time to retrieve the document from MongoDB is 1.6 milliseconds. The time to retrieve the document from APC cache is 0.2 milliseconds. That's nearly an order of magnitude faster for cache. In real terms, the cache can respond to requests in 1/10 the time, or respond to 10 requests for every 1 response from MongoDB. When network latency is introduced, the performance advantages are even more pronounced, and these results hold across many iterations. You can see that cache is consistently faster. Keep in mind that caching only helps when the same result is required again. It is impractical to build a cache with the flexibility of MongoDB's query mechanism. However, where frequent identical operations occur, it may make sense to introduce a complementary cache alongside MongoDB. In the resources file for this video, there is a list of complementary technologies to consider when caching is an option. This video explored the use of caching to make MongoDB applications even faster and more responsive. APC in the PHP programming language was used to demonstrate the performance benefits that are possible. This section started with an exploration of sharding and an example sharded deployment. The MMS tool was then used to deploy a 3-node replica set, and some key features were reviewed. It ended with a discussion of complementary cache technologies that can make MongoDB applications even more responsive. Congratulations on completing this video training series from PacT Publishing. Enjoy using MongoDB.